Good evening, and welcome to the Sleepy Geographer, a quiet corner of the internet where curiosity drifts gently alongside calm narration. If you're settling in for the night, perhaps with a cup of something warm or the lights already dimmed, you're in the right place. Tonight's journey takes us somewhere rather unusual, not across continents or oceans, but across time itself, to follow the slow, graceful dance of Earth's poles as they wander through the ages. Before we begin, I'd love to know where in the world you're listening from and what time it is there. It's always wonderful to imagine this little community scattered across the globe, each person lying still beneath the same turning planet. If you enjoy these sleepy explorations and they help you unwind, a gentle tap on the like button and a quiet subscribe helps more dreamers find their way here. And to those already subscribed, thank you, truly. I'll try my best not to make the story too interesting tonight, though if it happens to keep you awake, at least you'll be learning about one of the most subtle, beautiful motions our world performs. So, as Earth spins beneath us ever so slightly off balance, let's begin with a simple question. How can something as enormous as a planet ever truly lose its balance? Imagine for a moment standing at the top of the world, not metaphorically but literally, at the geographic North Pole. Beneath your feet, every direction leads south, yet that precise point, that single pivot on which our world turns, does not stay perfectly still. Over centuries and millennia, it drifts, describing tiny spirals across the surface of the globe. The same is true at the South Pole, its invisible twin on the other side of the planet. What does it mean then for Earth's axis to move? The answer is both simple and astonishing. Our planet spins like a top that is slightly dented, pulled by the gravity of the moon and the sun, nudged by the shifting weight of oceans, ice and air. The result is a slow rhythmic wandering, a celestial heartbeat measured not in seconds but in centuries. In geography, these quiet motions matter deeply. They define the maps we draw, the climate patterns we inherit, and even the direction our compasses try to follow. A change of just a few meters at the pole can alter coastlines over time, redirect winds, and reshape our understanding of stability itself. Tonight we'll explore the many ways Earth's poles have drifted and danced. We'll meet the invisible forces that guide them, the tides tugging at the crust, the slow rebound of ancient ice sheets, the breathing of the atmosphere, and the long wobbles that stretch across geological ages. This isn't a story of catastrophe or chaos, but of elegant motion, a planet finding its balance again and again. It's a reminder that even the ground beneath us participates in a slow, patient choreography that never truly ends. So settle in, breathe deeply, and let's follow the quiet path of the wandering poles, through the ages, across the sky, and into the very rhythm of the Earth itself. If you were to look at a globe and point to the very top, you might assume that's a fixed and eternal location, the North Pole. A comforting thought, perhaps. But the truth is, that point is only one of several kinds of north, and each has its own definition, its own way of wandering. The poles are not single, immovable spots on Earth. They are shifting ideas, pinned in place only by how we choose to measure them. Let's start with the simplest, the geographic pole, sometimes called the rotational pole. This is the point where Earth's axis, the imaginary line the planet spins around, pierces the surface. If you could trace that axis straight through the centre of the Earth, it would emerge at the opposite end as the South Pole. Together, they mark the pivot points of our planet's daily rotation. Every 24 hours, the entire globe turns once around that line, carrying everything. Oceans, continents, clouds, and you, in a grand, quiet circle. Now, this rotational pole is what defines latitude. The equator is halfway between these poles, and every degree of latitude north or south is measured relative to that spinning line. When we talk about the top of the world, this is the pole we mean, the true physical pole of Earth's rotation. Yet even this is not perfectly still, because the planet's mass isn't evenly distributed. The crust bulges slightly at the equator, ice caps melt, water shifts, and the atmosphere moves. The rotational axis wobbles gently, like a top that never spins quite symmetrically. Then there's another kind of pole altogether, the magnetic pole. This one has nothing to do with how the planet spins and everything to do with its magnetic field, which is generated deep within the molten outer core. The movement of iron and nickel in that liquid metal ocean creates an invisible magnetic field that surrounds the planet. Where those magnetic field lines plunge vertically into the Earth, we find the magnetic poles, and they too wander. The magnetic North Pole has been steadily trekking from northern Canada toward Russia for decades, at a rate that sometimes reaches more than 50 kilometers each year. For navigators, this matters. Compasses don't point toward the rotational pole but toward the magnetic one. That means the north your compass shows and the true north on your map are rarely the same place. The difference between the two is called magnetic declination, and it varies depending on where you stand on Earth. In some places, that difference might be only a few degrees. In others, it can reach 20 or more. A sailor or pilot who ignores it could easily drift miles off course. Then, above both of these, there's a third notion, the celestial pole. Imagine extending Earth's axis infinitely out into space. Where that line meets the night sky, that's the celestial pole, the point around which the stars appear to spin. For observers in the northern hemisphere, it lies near Polaris, the North Star, though not exactly at it. Over millennia, even this point drifts, tracing a slow circle in the heavens due to the long, graceful wobble of Earth's precession. Civilizations across history have used the sky's apparent pivot to mark time, orient temples, and align calendars. In this way, the poles are both earthly and cosmic, linking the dirt beneath our feet to the stars above. Now, if you've ever heard someone use the term true north, this refers to the direction along the Earth's surface that points straight toward the geographic North Pole, the axis of rotation, not the magnetic one. Cartographers rely on true north to make maps consistent, because the magnetic pole's restlessness would otherwise twist every chart over time. In practical terms, a good map shows both: true north, marked by a star or arrow, and magnetic north, marked separately with its degree of declination for the date the map was made. Over the years, that value changes, which is why maps and navigation systems must be updated. Otherwise, north slowly slides across your paper. So far, so straightforward. One pole for rotation, one for magnetism, one for the heavens. But things grow trickier when you realise that our entire coordinate system, the grid of latitude and longitude, is built on assumptions that Earth itself refuses to perfectly obey. The continents drift, the crust flexes, and the oceans rise and fall. To keep track of it all, geographers and scientists use something called a reference frame. Think of a reference frame as very careful, invisible scaffolding wrapped around the Earth, used to anchor every coordinate. It's a mathematical model of the planet's shape, position, and motion, constantly refined as we gather new data. The WGS-84, short for World Geodetic System 1984, is the one used by GPS. It tells your phone or car exactly how to translate signals from satellites into positions on a curved, moving Earth. But even WG-84 needs periodic updates, because the planet itself is dynamic. That's why newer frames like the International Terrestrial Reference Frame or ITRF go further by tracking how the crust itself shifts a few millimetres each year. It's like a living map that acknowledges Earth's breathing. In simpler words, a reference frame is our best guess at where here is, adjusted as often as reality demands. Without it, maps would slowly drift out of sync with the planet. Landmarks would seem to slide, GPS readings would misalign, and boundaries could subtly migrate. Not because the land moved underfoot, but because our coordinate system failed to move with it. You might wonder why such tiny movements matter. After all, if the poles slide a few meters this way or that over decades, who could possibly notice? But in geography, small shifts accumulate like grains of sand. They influence how we model the planet's spin, how we calculate time from the motion of the stars, and how satellites align to send signals across vast distances. Even climate research depends on knowing the poles precisely. When ice melts in one hemisphere, the redistribution of mass changes how the planet wobbles. Track those wobbles closely enough, and you can infer where water has moved, a quiet but powerful tool for understanding global change. It's humbling, really. The poles, those supposedly fixed points that define every map and every compass, are in constant motion. They reveal that north and south are not simple absolutes, but part of a grand, ever-adjusting system. Geography, in that sense, isn't about frozen lines or static coordinates. It's about keeping pace with a restless world, one that never stops spinning, tilting, and balancing itself anew, even while we sleep beneath its steady stars. Long before satellites, before lasers, before clocks could even count a second, humans already sensed that the sky and the earth were linked by an invisible rhythm. They noticed that the sun didn't rise from exactly the same point on the horizon each morning, nor set in precisely the same place at night. Over the course of a year, its path drifted northward and southward, tracing the seasons. The shadows it cast lengthened and shrank in predictable ways, yet never perfectly repeated themselves. In those subtle variations lay the first hints that our planet's orientation in space was not entirely constant. The earliest geographers and astronomers didn't have telescopes or satellites. Their instruments were far simpler: sticks, stones, and patience. A gnomon, for example, was nothing more than a vertical rod or pillar placed upright in the ground. By observing the length and direction of its shadow at noon, ancient observers could determine the sun's highest point in the sky, and thus their latitude. The Egyptians, Babylonians, Chinese, and Greeks all used versions of this humble tool. From it grew the first sundials, and with them a growing sense that time and geography were intimately connected. In ancient Greece, thinkers like Eratosthenes took this a step further. Around 240 years before the Common Era, he compared the sun's angle at two cities, Syene and Alexandria, on the same day of the year. From the difference in shadow lengths, he deduced not only that Earth was round, but even managed to estimate its circumference with surprising accuracy. His work depended entirely on geometry and observation, the first marriage of mathematics and the motion of the heavens to understand the planet below. Other cultures achieved equally remarkable precision without ever sharing a word of theory. Polynesian navigators learned to read the rising and setting points of stars, the shape of swells, and the drift of clouds to maintain position across thousands of kilometres of open ocean. In northern Europe, megalithic structures like Stonehenge marked solar and lunar alignments, effectively functioning as enormous seasonal clocks. All of these were, in their own way, early forms of geodesy, the science of measuring the shape and orientation of the Earth. As time passed, instruments became more refined. During the Islamic Golden Age, astronomers built precise observatories in places like Baghdad and Samarkand. They used transit instruments, simple yet elegant devices that allowed them to watch stars as they crossed the local meridian, the imaginary north-south line that runs overhead. By measuring the altitude of a star at its highest point, they could fix latitude more accurately than ever before. Their data improved maps, navigation, and even our understanding of the calendar. Centuries later, in Renaissance Europe, instruments such as the Meridian Circle and Zenith Telescope pushed this precision even further. A meridian circle was essentially a giant, finely calibrated ring mounted so it could rotate only in the north-south plane. Observers peered through its sights to record the exact moment and angle at which a star crossed the meridian. Combined with accurate clocks, themselves a triumph of geography and engineering, these measurements revealed not only latitude but also how the Earth itself might be shifting underfoot. When repeated over many years, tiny discrepancies began to appear. The poles, it seemed, were not as steadfast as once thought. By the 19th century, the field of geodesy had matured into a global enterprise. Surveyors connected vast regions with triangulation networks, chains of measured angles linking mountain peaks and towers. From India's Great Trigonometrical Survey to the transcontinental arcs in Europe and the Americas, humanity was stitching together the planet's geometry with mathematical thread. Yet even as maps grew more precise, something still refused to stay still. Observers found that latitudes measured decades apart didn't quite match. The discrepancies were small, sometimes mere meters, but real. The implication was profound. The Earth's axis, or the crust beneath our feet, was moving. Then came the 20th century, and with it a revolution in precision. Suddenly the stars weren't the only fixed points available. We began creating our own. Using very long baseline interferometry, or VLBI, scientists linked radio telescopes across continents, observing distant quasars billions of light-years away. These quasars are so far and so stable that they act as cosmic lighthouses, reference points against which the Earth's tiniest motions can be measured. By timing the arrival of radio signals from these quasars at multiple telescopes, separated by thousands of kilometers, geodesists could calculate the exact distances between observatories with millimetre accuracy. Around the same time, the rise of satellite geodesy brought even greater clarity. GNSS, the family of systems that includes the American GPS, Europe's Galileo, Russia's GLONASS, and others, created constellations of orbiting beacons continuously broadcasting their positions. When a receiver on Earth picks up signals from several satellites, it can calculate its location. But, more importantly for scientists, it also provides data about how the planet itself is moving. The relative motion between satellites and ground stations reveals the drift of tectonic plates, the rise of mountains, and the shifting of the poles. Then came satellite laser ranging, an exquisitely delicate method where pulses of light are fired at satellites equipped with special reflectors. The time it takes for the light to return to Earth tells scientists the distance to the satellite with remarkable precision. Combine those data from multiple locations, and you can see the entire planet flex and wobble as if breathing. Another leap forward arrived with gravity missions like GRACE, the Gravity Recovery and Climate Experiment. 2 satellites followed each other in orbit, measuring minute changes in the distance between them as they passed over regions of slightly stronger or weaker gravity. When a large ice sheet melted or groundwater levels changed, the mass redistribution subtly altered Earth's gravitational field, and the satellites noticed. These shifts, mapped over time, showed not only how water moves across the globe, but also how those changes influence the planet's rotation and pole position. It's astonishing to think that the wanderings of the poles, which once could only be guessed at from shifting star paths, can now be tracked to within millimetres. The distance from London to Tokyo can be measured to the thickness of a fingernail, and the drift of the rotational pole can be followed as it meanders through loops, no larger than a few metres each year. To a sleepy observer, Those numbers might seem trivial, but they represent a triumph of human patience and ingenuity. What makes it even more beautiful is the continuity of the story. The gnomon shadow, the meridian circle, the radio telescope, the orbiting satellite. They all serve the same quiet purpose, to understand how the Earth moves through space and how that motion shapes our world. What began as curiosity about why a shadow shifted on the ground has grown into a planetary-scale conversation between instruments scattered across continents and spacecraft floating hundreds of kilometers above the atmosphere. In a way, modern geodesy is a form of listening to the planet's faintest murmurs. Every wobble, every tilt, every slow drift of the poles is a whisper from Earth about its inner workings. These signals tell stories of melting ice, restless plates, and the pull of distant bodies in space. Through technology and patience, we've learned to translate those whispers into understanding. So next time you glance at a compass or trace a line on a map, remember that behind that simple direction lies a vast network of quiet watchers, instruments old and new, from sundials to satellites, all keeping track of a planet that is never perfectly still. And in their precision, we find not rigidity, but grace, a reminder that motion, even the smallest kind, is what gives our world its rhythm. Every night as the planet turns, the stars seem to wheel around the sky in perfect order. To the patient eye, there's a quiet rhythm in it. Stars rise, arc and sink beneath the horizon with astonishing precision. But what's easy to miss, because it happens so slowly, is that even this grand rotation changes over time. The entire sky itself drifts, as if the heavens were slowly tilting their head. This long, majestic sway is called precession, and it takes roughly 26,000 years to complete a single cycle. To imagine it, picture a spinning top on a table. When it's spinning fast, the top stands upright, but as it slows, the axis begins to wobble, tracing a gentle circle in the air. Earth behaves in much the same way. It's spinning rapidly, once every 24 hours, yet it isn't perfectly symmetrical. The equatorial bulge caused by the planet's rotation gives the sun and the moon something to tug on. Their combined gravitational pull acts on that bulge, and the result is a slow, stately wobble of Earth's axis in space. The planet doesn't tip over dramatically, but rather describes a wide cone, with its axis sweeping across the sky like the motion of a pendulum so vast that only centuries reveal its curve. If you could speed up time, you'd see the North Pole tracing a wide circle against the backdrop of distant stars. At present, that circle takes about 26,000 years to complete. Right now, the axis points very close to a bright star called Polaris, which is why sailors and stargazers call it the North Star. But that hasn't always been the case. Around 5,000 years ago, when the pyramids were being built, the star Thuban in the constellation Draco marked the northern sky's centre. In about 12,000 years, that honour will pass to Vega, a brilliant blue-white beacon in the constellation Lyra. The heavens may look timeless, but the compass of the cosmos is ever turning. This wandering of the sky has consequences far beyond astronomy. Because the planet's axis slowly rotates, the timing of the equinoxes and solstices drifts through the calendar as well. This is why ancient civilizations constantly refined their calendars. They were trying to keep human time in step with the cosmic clock. The Egyptians noticed that their calendar gradually fell out of sync with the flooding of the Nile, which was linked to the star Sirius rising before dawn. The Greeks and Romans later recognized the same drift and adjusted their systems accordingly. Precession subtly rewrites the sky schedule, so that the stars marking the start of spring today won't be the same ones that marked it in the distant past. The Earth's equatorial plane, because of this wobble, also moves relative to the background of the stars. The intersection points of that plane with the sun's path, called the equinoxes, slide slowly westward around the celestial sphere, completing their loop once every 26 millennia. Ancient astronomers noticed this and called it the precession of the equinoxes. To them, the heavens were supposed to be immutable, so the discovery that even the stars shifted over the ages was nothing short of revolutionary. It was the Greek astronomer Hipparchus, in the 2nd century before the Common Era, who first detected it by comparing his observations with those recorded more than a century earlier. The tiny difference he found in star positions revealed a motion so slow that most people would never notice it in a lifetime. Over time, the understanding of precession influenced everything from astrology to architecture. Temples, pyramids, and megaliths aligned to once significant stars slowly lost their precision as the heavens shifted. What was once a perfect alignment to a star at rising became off by a degree, then two, then more. To ancient builders, it might have seemed the stars themselves were drifting away, a poetic and unsettling truth. Even myths adapted to this change. In some cultures, stories of the world tree or cosmic axis being shaken or rerouted may echo distant memories of this celestial migration. The change in pole stars also affected navigation. For early travellers who used the night sky to find their way, the North Star has always been a symbol of steadiness, yet that steadiness is, in truth, a temporary gift. Mariners of a far future age will look up and see a different guide in the northern heavens. They'll still call it north, but it will point to a slightly different patch of space, because Earth's axis will have continued its graceful journey. Precession doesn't alter the tilt of the planet, only the direction that tilt points. The angle, about 23.5 degrees, remains roughly constant, but the orientation of that tilt rotates slowly like a gyroscope's axis. This means that, on long timescales, the patterns of sunlight on Earth shift. The Northern Hemisphere's winter solstice, for example, now occurs when the Earth is closest to the Sun, but thousands of years from now it will occur when Earth is farthest. These variations, combined with other orbital cycles, help shape the rhythm of ice ages and interglacial periods. Our planet's climate, its coastlines, and even the distribution of ecosystems subtly respond to the geometry of this cosmic dance. Because precession unfolds so slowly, it's easy for myths and misconceptions to sprout around it. Some claim that Earth's poles suddenly flip, or that the planet could topple overnight. In reality, such cataclysmic shifts don't occur in the realm of geography. The magnetic field can reverse over geological timescales, and it has. But the geographic poles, the points around which the planet physically spins, move with dignified restraint. The wobble that redirects the celestial pole unfolds so gently that even entire civilizations rise and fall before the stars noticeably change their places. If Earth's axis were a dancer, it would move with the patience of stone. There's something comforting about that slowness. Precession reminds us that change doesn't always arrive as a shock. Sometimes it's a gradual drift, measured in thousands of lifetimes. The North Star we know is just one in a long lineage, each taking its turn at the centre of our night sky. And though the stars seem eternal, their alignment with Earth is as transient as everything else. When you look up tonight, the stars might seem fixed, their positions eternal and unmoving, but in truth, they're part of a slow choreography that's been unfolding since long before humans learned to watch it. The axis of our planet continues to trace its vast circle, Polaris slowly stepping aside for its successors. It's an exquisite rhythm, the steady breathing of the cosmos, reminding us that even the sky, in all its apparent stillness, is quietly turning. If precession is the grand sweeping waltz of the planet's axis, then nutation is the delicate, unpredictable sway that decorates it, the small ripples dancing on top of the slow, 26,000-year motion. The word comes from the Latin nutare, meaning to nod, and that is precisely what Earth does, a quiet, rhythmic nodding motion as it spins and wobbles through space. Imagine Earth's axis as a pencil balanced on the tip of your finger, tracing a wide circle as it precesses. Now picture that same pencil trembling ever so slightly as it moves, adding tiny oscillations to the larger path. These smaller tilts are the nutations, little dips and rises layered on the big wobble. While precession is smooth and predictable, nutation is intricate and textured, with components that repeat over months, years, or decades. The most important cause of nutation is the Moon. Our lunar companion doesn't orbit Earth in a perfectly steady way. Its path is slightly tilted relative to Earth's equator and also changes direction over time. Because of that, the Moon's gravitational pull on our planet is not constant. Sometimes it tugs a little more northward, sometimes southward, sometimes at an angle. These varying tugs cause Earth's axis to dip and rise by a few arcseconds, a tiny angle far too small for the naked eye to detect. But over time, these nods add up to a complex, graceful pattern. The principal nutation cycle has a period of about 18.5 years, driven by the motion of the Moon's orbital nodes, the points where its orbit crosses the ecliptic, or the plane of Earth's orbit around the Sun. As those nodes slowly regress or drift westward, the direction of the Moon's pull on the equatorial bulge of Earth changes. This makes the axis trace a slight unevenness along its path, like an embroidery of gentle waves around the circle of precession. Yet the Moon is not acting alone. The Sun also joins in, adding its own smaller but steady influence. The interplay of these two bodies, one near and swift, the other far and slow, creates an intricate mixture of frequencies, each corresponding to a different nutation term. Some repeat annually, others over months, and some over decades. The resulting motion is an exquisite cosmic chord, each note faint but measurable. For most of human history, these tiny variations went unnoticed. Precession itself was already subtle enough, and nutation's scale, mere seconds of arc, was far beyond the reach of early instruments. It wasn't until the 18th century that the phenomenon was firmly described, thanks to the meticulous observations of the English astronomer James Bradley. He was studying the apparent motion of stars when he discovered two effects that together revolutionized astronomy: the aberration of starlight caused by Earth's motion around the Sun, and nutation caused by the Moon's shifting pull. His careful records revealed that the celestial pole's position didn't follow a perfect circle, but a wavy line. Each crest and trough matched the rhythm of the lunar cycle. Bradley's discovery gave astronomers a more precise model of the sky's motion, and it remains one of the quiet triumphs of observational science. It showed that even in the vast machinery of the cosmos, the tiniest forces can leave a signature if you're patient enough to watch. For geographers and cartographers, nutation might seem like an esoteric curiosity. After all, what difference does a few arcseconds of tilt make on a spinning planet? The answer lies in the pursuit of precision. Modern mapping, navigation, and satellite operations all rely on exact knowledge of Earth's orientation at any given moment. A small shift in the axis changes how ground positions are projected into space. If uncorrected, these shifts could accumulate into errors large enough to matter in global positioning systems, intercontinental surveying, or even climate modelling. In practical terms, the effects of nutation are built into the mathematical models that define Earth's reference frames, the invisible scaffolds that support all geographic coordinates. When scientists calculate orbits, track tectonic motion, or align laser ranging instruments, they must account for the exact orientation of Earth's spin axis for that specific date and time. Even a minuscule deviation alters how we perceive the location of satellites or ground stations by a few centimetres, which for a field like geodesy is the difference between excellence and uncertainty. The precision of these corrections is astonishing. Space agencies and observatories maintain detailed tables, nutation models, describing hundreds of separate terms, each corresponding to a periodic influence from the Sun, Moon, and even planets. Every wiggle and oscillation is logged, computed, and fed into the algorithms that guide satellites, synchronize time, and update maps. It's as if we've learned to choreograph Earth's smallest twitches so that our instruments can dance perfectly in step with them. This level of precision has real-world consequences. Consider a satellite orbiting hundreds of kilometers above Earth, tasked with monitoring sea level rise or tracking gravitational variations. The data it collects are referenced to the planet's center of mass and orientation in space. If the axis of rotation tilts even slightly due to nutation, the satellite's position relative to Earth changes, which can affect how we interpret its readings. Correcting for nutation ensures that what the instruments measure is the movement of the oceans, not the subtle nodding of the world beneath them. Nutation also has a hand in timekeeping. Because Earth's rotation defines the length of a day, and that rotation is influenced by gravitational torques, the small periodic wobbles introduced by nutation affect how we measure time at the most refined levels. Atomic clocks remain perfectly steady, but the planet does not. Astronomers and geodesists therefore maintain continuous observations to align atomic time with Earth's orientation, blending cosmic precision with human need. There's something quietly poetic in all this. The moon, that serene light we associate with tides and romance, is also the source of these tiny physical undulations that keep geographers awake with calculations. Each lunar orbit leaves a subtle trace on the tilt of the Earth, like a gentle hand nudging a spinning globe. The sun adds its steady pressure, and the whole system becomes a dialogue between forces, a conversation that has been unfolding for billions of years. If you could speed up time, you would see the planet's axis waver and tremble, tracing looping curves in space. But to the human eye, the effect is invisible, smoothed out by the immense scale of time, and perhaps that's part of its beauty. Nutation is the quiet background rhythm of the Earth's motion, one that must be listened to through mathematics rather than sight. Every map, every GPS reading, every satellite photo owes a silent debt to this hidden nodding. It's a reminder that even the most solid-seeming things, the ground beneath us, the pole of the planet, are in conversation with the heavens. Our instruments capture those whispers, our equations give them meaning, and in return we gain a clearer picture of the delicate balance that keeps our spinning world steady. The next time you glance at the moon, know that it is not just a companion in the night, but a participant in a subtle cosmic dance, one that gently tips the axis of an entire planet, reminding us that stillness, even for the Earth itself, is only ever an illusion. Every few tens of thousands of years, Earth subtly rewrites its own climate map, not through volcanic eruptions or asteroid impacts, but through gentle shifts in the way it moves around the sun. These changes are small, almost imperceptible from one generation to the next, but over time they steer the rhythms of ice and warmth, desert and forest, drought and rain. The patterns are known as the Milankovitch cycles, named after the Serbian mathematician Milutin Milankovic, who spent the early 20th century calculating how variations in Earth's orbit and tilt could influence the distribution of sunlight across the globe. His work eventually revealed that the shape of Earth's path, the angle of its lean, and the direction it points in space act together as a set of slow cosmic dials, the great pacemakers of climate. The first of these dials is eccentricity, the shape of Earth's orbit around the Sun. Most of the time, we imagine that orbit as a perfect circle, but in truth it gently stretches and squeezes over cycles of about 100,000 years. Sometimes the orbit is almost circular, keeping the Earth at nearly the same distance from the Sun throughout the year. At other times, it becomes more elliptical, meaning there is a noticeable difference between the closest point, called perihelion, and the farthest, aphelion. When the orbit is more eccentric, the contrast between the seasons becomes slightly greater, not because the planet's tilt changes, but because its distance from the Sun varies more dramatically. Next comes obliquity, the tilt of Earth's axis. Right now, the axis is inclined about 23.5 degrees relative to the plane of its orbit, but that angle itself oscillates between roughly 22 and 24.5 degrees over a period of about 41,000 years. A greater tilt means more extreme seasons, hotter summers and colder winters, especially at high latitudes. A smaller tilt softens the seasonal contrasts, keeping the polar regions cooler year-round. When the tilt is low, snow and ice that accumulate in winter are less likely to melt completely in summer, allowing glaciers to persist and expand. The third factor, precession, is the slow wobble of Earth's axis, the same motion described earlier when discussing the wandering of the poles. Precession changes the timing of the seasons relative to Earth's position in its orbit. Right now, for example, the Northern Hemisphere's summer happens when the Earth is farthest from the Sun, moderating temperatures slightly. But in about 10 to 12,000 years, the wobble will reverse that relationship. The Northern Hemisphere's summer will occur when Earth is closest to the Sun, making summers hotter and winters colder. Each of these cycles operates on a different time scale, and together they interact in intricate ways. Sometimes they align to amplify one another, at other times they cancel out. Milankovitch painstakingly calculated how the combined effect of these orbital changes altered the amount of sunlight, or insolation, reaching different latitudes through the year. He showed that even small variations in sunlight at high northern latitudes could tip the balance between ice growth and ice melt, initiating or ending an ice age. For decades, his theory was treated with cautious interest. Then, as scientists began drilling into ocean sediments and ice cores in the latter half of the 20th century, they uncovered rhythmic patterns in climate data, cycles of warmth and cold that matched Milankovitch's calculations almost perfectly. The layers of dust, fossil shells and trapped air bubbles told a consistent story. When the Earth's orbit became more elongated, or its tilt lessened, or its precession shifted the seasons just so, glaciers advanced. When the geometry tilted the other way, the ice retreated. The last 2.5 million years of Earth's history, the Quaternary period, have been shaped by these oscillations. Roughly every 100,000 years, vast ice sheets have crept down from the poles, sculpting continents like slow-moving rivers of stone. They carved valleys, dammed lakes, and scoured plains. At their height, sea levels fell by more than 100 meters as water was locked up in frozen form. Coastlines stretched far beyond their modern bounds, connecting islands and continents. You could have walked from what is now Britain to France, from Siberia to Alaska, and from Australia to New Guinea. These vanished land bridges were the highways of early migration, their routes now drowned beneath the sea. When the ice receded, the planet redrew itself again. Forests expanded, deserts retreated, and rivers found new paths. Rain belts shifted north and south with the changing patterns of sunlight, leaving behind fossil dunes where savannas once flourished. The Sahara, which today seems timeless in its aridity, has repeatedly transformed into a green landscape of lakes and grasslands when the orbital cycles favoured stronger monsoons. Each alteration in the planet's motion rippled across geography, changing not only the map of coastlines but the very distribution of life. In this way, the Milankovitch cycles serve as the metronome of Earth's environmental history. They don't create climate on their own. Rather, they modulate it, nudging complex systems into new states. Ice and ocean, atmosphere and vegetation all respond to the faint changes in solar energy. When feedbacks amplify those changes, for instance, when expanding ice reflects more sunlight and cools the planet further, the result is a cascading transformation. Geography, seen over hundreds of thousands of years, becomes a moving picture of frozen and thawed worlds. For geographers, this connection between orbital geometry and physical landscape is deeply elegant. It shows that climate isn't just a meteorological phenomenon, but a cartographic one. An agent that draws and erases the boundaries of ecosystems and coastlines. The scars of ancient ice sheets still mark the land. U-shaped valleys in Scotland, polished granite in Canada, fjords in Norway. These are not merely scenic features, they're geological memories of celestial mechanics at work. Even today, though we live in a comparatively warm interglacial period, the same cycles continue to tick quietly in the background. If left to themselves, they would eventually usher in another ice age tens of thousands of years from now. But human influence, the release of greenhouse gases and the reshaping of landscapes, has altered that balance, delaying or perhaps cancelling the next great freeze. The planet's climate now responds not only to the slow rhythms of space but also to the swift hands of its inhabitants. There's a kind of calm wonder in realising that the ice ages and interglacial worlds weren't accidents, but outcomes of predictable celestial geometry. The continents we know, the migration routes our ancestors took, the shapes of our deserts and forests, all of these were partly dictated by the tilt and sweep of our orbiting planet. The Milankovitch cycles remind us that geography is a story written in two languages at once, one of rocks and rivers, and one of stars and angles. When you look at a map of Earth, frozen in a single moment, it's easy to forget that it is only a snapshot of an ever-changing design. Coastlines are temporary, deserts are seasonal, and even the position of the tropics drifts with time. All of this, the migration of biomes, the ebb of ice, the rise of seas, is part of an ancient rhythm driven by sunlight that waxes and wanes with cosmic precision. And in that rhythm lies a kind of peace, the knowledge that Earth, restless as it may seem, has always been following the same quiet beat, circling the sun in its long, graceful dance. In the late 19th century, an American astronomer named Seth Carlo Chandler sat with years of star positions and a quiet suspicion that something subtle was hiding in the data. Astronomers had long known about precession and nutation, those grand and graceful changes in Earth's orientation. But Chandler noticed a smaller, quicker quiver superimposed on the larger motions, a gentle sway of the rotation axis itself with a period of roughly 14 months. He announced the discovery in the year 1891, and the phenomenon has been known ever since as the Chandler wobble, Earth's free swing, a natural resonance of a spinning elastic planet. To picture it, imagine a child's top that is spun so smoothly it stands nearly upright. Even a well-spun top never holds itself perfectly still. It makes a tight, slow circle as it precesses. Now imagine an extra independent shimmy riding on that bigger motion, like a sleepy nod the top cannot help but give. That is the Chandler wobble, a free nutation of Earth, not forced by any single clock in the sky, but excited and sustained by the planet's own shifting fluids and winds. Its period is a shade longer than a year, about 14 months, corresponding to roughly 433 days, and its amplitude at the pole is small, on the order of a few meters traced on the ground. For most of human activity, that seems negligible. For the sciences that define where and when with exquisite care, it is a feature that must be watched every day. Why should a seemingly solid planet wobble at all? The answer lies in the fact that Earth is not a rigid sphere. It is slightly flattened at the poles, elastic in its rocks, viscous in its mantle, liquid in its outer core, and covered by moving oceans and an ever-breathing atmosphere. A truly rigid, perfectly symmetrical body could spin without a free wobble. But a real Earth, with its small departures from symmetry in its deformable interior, has a natural mode of motion, a free swing, that shows up as this 14-month wiggle. The amplitude waxes and wanes as different processes kick the wobble, then let it decay, then kick it again. Those kicks often come from the air above us and the water around us. The atmosphere carries enormous angular momentum. When strong winds roar across the Pacific or a persistent pressure system parks over a continent, the mass of the air and its motion change the way momentum is shared between the atmosphere and the solid Earth. A tiny fraction of that adjustment shows up as a nudge to the rotation axis. Likewise, the oceans shift vast quantities of water through currents and seasonal changes. As water piles up along one coast and draws down along another, the distribution of mass on the planet's surface changes. The solid Earth responds, minutely but measurably. The combined effect of atmosphere and oceans produces an annual wobble, tied to the seasons, and it also excites the free Chandler wobble, sometimes strengthening it, sometimes letting it fade. There is a pleasing detective work in untangling these motions. Geodesists take observations from radio telescopes, satellites, and laser ranging systems and separate Earth's polar motion into a handful of components. A steady, long-term drift of the pole, an annual term linked to the march of seasons, and the Chandler term with its 14-month beat. The annual term follows the rhythm of monsoons, storm tracks, and ocean gyres. The Chandler term behaves like a bell after a distant tap, ringing with its natural frequency, gradually damping unless stirred again. Together they make the pole trace a tiny looping path, a lopsided rosette of a few meters in radius, centered not quite where you might expect. If the path is so small, why does it matter? Because modern geography operates at millimetre scales. Survey networks that define property boundaries, bridges whose spans are guided by GNSS receivers, and spacecraft whose instruments measure sea level to a few centimetres, all depend on knowing Earth's orientation at the moment of measurement. The Chandler wobble is one of the ingredients used to compute the Earth orientation parameters, the quietly crucial numbers that tell us how the planet is oriented in space and how fast it is turning. Without those parameters, longitude and latitude would be ever so slightly misprojected, and the difference would accumulate into real errors on the ground. Consider a satellite tasked with tracking the height of the ocean. It orbits with respect to Earth's centre of mass, and its altimeter reports the distance to the sea surface below. But if the rotation axis has nudged a few centimetres relative to the satellite's reference frame, the geometry changes. To interpret the data correctly, analysts must remove the effect of polar motion, including the Chandler wobble, so that the remaining signal is truly about water, not about the planet's free swing. In a similar vein, ground stations used for GNSS, satellite laser ranging, and very long baseline interferometry record positions through time. Their coordinates are expressed in reference frames that assume a known Earth orientation. Feed in a slightly wrong orientation, and you can misplace a station by centimetres or skew a velocity estimate by fractions of a millimetre per year. For continental drift and sea level studies, that is the difference between a clean result and a fuzzy hint. Timing too feels the wobble's touch. The length of day is not perfectly constant. Winds, currents, and exchanges between the core and mantle cause tiny accelerations and decelerations, while the Chandler wobble is primarily a change in orientation rather than speed. The same geophysical processes that excite it also jostle Earth's rotation rate. The result is that astronomers and timekeepers monitor Earth's spin continuously and publish corrections so that civil time, satellite time, and astronomical time remain in useful harmony. When you hear about the need to reconcile atomic clocks with the turning of the Earth, you're overhearing a conversation that also involves the wobbling of the pole and the breathing of the atmosphere. There's another, more philosophical reason geographers care. The Chandler wobble is a reminder that place is not just latitude and longitude printed in ink. Place is defined in a living, moving frame. Reference frames, such as the International Terrestrial Reference Frame, treat Earth as a patient that is always shifting, always healing from the last ice age, always being pressed by winds and water. The wobble is one of the vital signs. When its amplitude changes, we learn something about the balance of energy in the atmosphere and oceans. When it drifts, we learn about mantle viscosity and the elasticity of the crust. The wobble turns the Earth into its own instrument. Chandler did not have satellites or lasers. He had patience and star catalogues. After his work, astronomers and geodesists refined the picture. They showed that the wobble's period is a little shorter than the year, that the path of the pole is not a tidy circle but an ellipse, and that the amplitude is not constant. In some decades the wobble swells. In others, it nearly disappears. Those changes point to the strength of seasonal circulation and the ocean's response, much like the varying ring of a gong tells you about the strike in the material. Think again of the dozing top. It stands almost upright, spinning with steady poise. Now and then a breath of air nudges it, and a faint, almost dreamy sway appears. It is not a lurch, not a stumble, just a soft, persistent motion that tells you the top is real and responsive. Earth, too, wears its responsiveness plainly for those who know how to look. On maps, the wobble does not show. Coastlines pay it no mind. But in the instruments, in the numbers that define the scaffolding behind every map and chart, the wobble is always there. An elegant imperfection we account for so that everything else can be crisp. Perhaps the quiet wonder of the Chandler wobble is that it links weather to wear. A winter of unusual winds can leave fingerprints in the path of the pole months later. An ocean that sloshes differently sends its report in the same delicate script. The 14-month beat is therefore not just a curiosity, but a conversation between sky, sea, and stone. When geographers and navigators correct for it, they are not tidying up an error. They are acknowledging a truth. The Earth is alive with motion, even when it seems fast asleep, and so the planet turns, a little off-centre, a little elastic, composed of solids that flow and fluids that push back. It keeps its balance not by resisting every touch, but by yielding a little, swaying a little, then settling again. That small, persistent nod, the Chandler wobble, is the planet's way of saying yes, I am steady, and yes, I am also softly in motion. Like a dozing top, Earth holds its line by the grace of a gentle sway. When you imagine the poles moving, it's easy to picture the entire planet tipping one way or another. But in the slow language of geology, there's more than one way for that to happen. Sometimes it's the Earth itself that changes orientation beneath its spin, and sometimes it's the continents that drift, giving the illusion of wandering poles. These two ideas, true polar wander and apparent polar wander, describe different kinds of motion, yet both reveal a simple truth. Our planet is never entirely still, even over the longest stretches of time. Let's begin with true polar wander, often shortened to TPW. This is what happens when the entire solid shell of the Earth, the crust and mantle together, reorients relative to the planet's spin axis. The poles, in this case, do not move across the surface of the Earth because of tectonic drift or plate motion. Instead, the the entire outer layer of the planet shifts around the core, like the peel of an orange slowly sliding around the fruit inside. The spin axis itself remains fixed in space, but because the crust and mantle move, the geographic positions of the North and South poles appear to migrate across the globe. It's as though the Earth were adjusting its weight to stay balanced as internal masses shift deep within. Why would a planet do such a thing? The answer lies in distribution of mass. Earth's rotation naturally tries to position its greatest bulk along the equator, where centrifugal force is strongest. If large-scale changes inside the mantle, for example upwellings of hot rock or the build-up of massive mountain ranges, redistribute that mass unevenly, the entire planet can slowly roll to restore equilibrium. It's a self-correcting behaviour, much like a spinning figure skater adjusting posture to maintain balance. Over millions of years, the outer shell of the planet realigns so that the heaviest parts lie closer to the equator and the lightest parts shift toward the poles. Geologists believe this has happened several times in Earth's deep past. Evidence suggests that during the late Precambrian, roughly 700 million years ago, the planet may have undergone a major true polar wander event, moving its entire outer shell by as much as 60 degrees relative to the spin axis. Such a shift would have profoundly altered global geography, dragging continents and oceans into new latitudes and dramatically reshaping climates. But because it occurs over tens of millions of years, it is not a sudden or catastrophic motion, more like the planet slowly rolling in its sleep. Then there's apparent polar wander, or APW. This one is trickier because it's not the planet turning under its axis, but the continents themselves drifting across its surface. The poles stay where they are relative to the rotation axis, but because the continents are always on the move, each landmass tells a different story about where it believes the poles to be. Imagine standing on a slowly moving raft, pointing toward a distant lighthouse. As the raft drifts, it may look as though the lighthouse is shifting position, when in reality, it's you who's moving. Apparent polar wander is the geological version of that illusion. To tell these two motions apart, the real and the apparent, scientists needed a kind of geological compass, something that could record the ancient direction of Earth's magnetic field. That compass turned out to be buried in the rocks themselves. When molten rock cools and solidifies, magnetic minerals inside it, such as magnetite, align with the planet's magnetic field at that time and place. Once locked in, these minerals preserve a permanent record of the direction and intensity of that ancient field. This property, known as paleomagnetism, lets geologists determine the latitude at which the rock formed and the orientation of the continent relative to magnetic north. By collecting paleomagnetic data from rocks of different ages on the same continent, scientists can trace an apparent polar wander path, a curve showing how the magnetic pole seems to have moved over time. But when you compare those paths between continents, an interesting pattern appears. If all continents show identical pole paths, it implies that the poles truly moved, a case of true polar wander. But if each continent has its own distinct path, the explanation must be continental drift. In other words, apparent polar wander reveals the slow choreography of tectonic plates. These paleomagnetic clues were among the first solid pieces of evidence supporting the theory of plate tectonics. In the mid-20th century, when scientists noticed that apparent polar wander paths for Europe and North America could be aligned only if the continents were brought back together, it became clear that the continents had once shared the same geography and later drifted apart. What seemed to be the poles moving was really the continents taking their time across the planet's surface. The implications of both kinds of wander are vast. They not only describe how continents travel, but also how entire climates migrate. A region that sits under tropical sun today might once have been locked under polar ice. Paleomagnetic and geological evidence together show that deserts, forests and ice caps are all temporary tenants of latitude. When supercontinents such as Rodinia, Gondwana or Pangaea assembled and later broke apart, they didn't just rearrange coastlines, they altered the distribution of light and heat around the globe. Rain belts followed the new equators, glaciers advanced when new poles emerged. Geography became a kind of living map, redrawn by the steady turning of the world's crust. True polar wander events, though rarer than ordinary plate motion, could have triggered some of the most dramatic environmental changes in Earth's history. If continents were abruptly shifted toward higher latitudes, global weather patterns and ocean currents would have reorganized. Some researchers have suggested that such motions may have contributed to episodes of snowball Earth when ice spread nearly to the equator. Whether or not that's true, the concept illustrates how closely planetary motion and climate are intertwined, a reminder that geography operates on both human and geological timescales at once. The study of ancient magnetic fields continues to refine our understanding of these wanderings. Satellites and supercomputers now allow geophysicists to simulate the planet's magnetic history, reconstruct the positions of continents through time, and even estimate how fast the crust has tilted relative to the spin axis. In modern reconstructions, we can watch Pangaea drift apart, Africa rotate slightly northward, and India race toward Asia at breakneck speed, all while the poles trace elegant looping paths across the map. These animations are not artistic guesses. They're grounded in the magnetic whispers of rocks, the frozen memories of Earth's invisible compass. There's a quiet poetry in realizing that the magnetic field, which guides migrating birds and modern compasses alike, has also guided geologists through the corridors of time. Each basalt flow, each ancient lava bed, carries a sliver of direction, a snapshot of where north once was. Add enough of these snapshots together, and you can watch the continents glide, the poles wander, and the planet itself slowly recompose its face. Whether it's true polar wander or apparent polar wander, both describe the same idea in different ways, that Earth is restless, adjusting, balancing itself through deep time. Its outer shell spins and shifts atop a molten heart, its magnetic field flickers and flips, and its continents roam like sleepwalkers across an unhurried globe. The maps of today are merely a passing arrangement, a brief pause in a 4 billion-year dance between stone and space. And while we may call one motion true and the other apparent, in the end both remind us that the ground beneath our feet is every bit as alive and every bit as changeable as the sky above. If you could look at Earth from space not as a solid planet, but as something alive and flexible, you'd see it bending, swelling and breathing in response to the weight of ice and water. The ground itself rises and falls like a slow tide, responding to how mass moves across its surface. And as that weight shifts, from melting glaciers to draining aquifers, even the planet's spin adjusts, the poles inching in new directions. The world we stand on is not the unyielding globe we imagine, but a viscoelastic one, part solid, part fluid, part memory. The term viscoelastic may sound like something you'd find on a lab label, but it captures the essence of Earth's nature perfectly. The planet's crust behaves elastically in the short term. It can flex and spring back slightly, but over long spans of time, it flows like very thick syrup. The rocks of the mantle are not brittle blocks, but an ultra-slow-moving sea of solid material that creeps under stress. This means that when great ice sheets form and melt, the planet doesn't merely shrug them off. It slowly sags and rebounds, carrying the memory of past weight for thousands of years. During the last ice age, vast domes of ice smothered North America, Northern Europe, and parts of Asia. The Laurentide ice sheet alone, which covered much of Canada and the northern United States was several kilometres thick. That much ice weighed trillions of tons. Under such enormous mass, the crust beneath it sank, while areas around the edges bulged upward, like the brim of a bowl pressed by a heavy hand. When the ice began to melt roughly 12,000 years ago, the pressure lifted and the land began to rise again, a process still continuing today. This is called post-glacial rebound, and you can measure it with GPS stations that record regions of Scandinavia, Canada, and Alaska rising by centimetres each year. But Earth's response is not symmetrical. As land once buried by ice rises, nearby regions may actually sink, redistributing mass across the planet's surface. The oceans respond too. As water from melted ice sheets flows into the sea, it doesn't spread evenly. Instead, gravity draws it preferentially towards some regions and away from others. Massive ice sheets exert a gravitational pull on nearby oceans. When that ice melts, the pull weakens and water migrates toward the opposite hemisphere. The result is a complex, uneven rise in global sea level, what scientists call sea level fingerprints. The pattern depends on where the mass is lost. Melt Greenland's ice and the ocean around it actually drops a little while faraway coastlines rise. Melt Antarctica and the northern hemisphere's oceans swell higher. Every ton of water that moves alters the balance just slightly, and Earth's rotation notices. As these masses shift, the planet's moment of inertia, its internal distribution of weight, changes. Like a figure skater extending or pulling in their arms, Earth's spin adjusts to stay balanced. The rotation rate can vary minutely, and the poles, the very axis of that rotation, drift in response. This isn't a guess, it's been measured. Over the 20th century, the average position of the North Pole moved roughly 10 centimetres per year toward the meridian of Greenwich, tracing a slow path across the Arctic. Satellite observations and gravity measurements now reveal that part of that drift comes directly from melting ice in Greenland and from large-scale groundwater depletion in Eurasia and North America. When billions of tons of water are pumped from underground and end up flowing into the sea, the mass redistribution ever so slightly tips the planet. It's a humbling thought. A farmer's irrigation well in India, a shrinking aquifer beneath California's Central Valley, or the gradual retreat of a glacier in Greenland each make an infinitesimal contribution to a planetary scale rebalancing act. On their own, these are barely whispers of change, but together they alter how the planet spins beneath the stars. Earth's axis drifts by only a few centimetres a year, yet that small shift reflects the combined influence of oceans, ice, rivers, and human activity. Geography, it seems, is written not only in the shapes of continents, but also in the subtle movement of weight. The science behind detecting these changes has become breathtakingly precise. Satellite missions like GRACE, the Gravity Recovery and Climate Experiment, launched in the early 2000s, have made it possible to weigh the planet's shifting water. GRACE tracked minute changes in gravity by measuring the distance between two satellites following each other in orbit. When they passed over a region where mass had increased, say, after heavy rainfall or an ice surge, Earth's stronger gravitational pull slightly altered their spacing. The result was a global time-lapse portrait of Earth's breathing. Ice melting here, aquifers draining there, oceans swelling elsewhere. Those same data revealed how polar drift is tied to the geography of water. When the ice in Greenland melts more rapidly, the pole's path bends subtly toward that region. When drought and groundwater loss intensify in the mid-latitudes, the direction tilts accordingly. This connection turns the abstract idea of polar motion into something tangible and immediate. Each droplet of water carries mass, and when enough of those droplets move, the planet must respond. Think of Earth as an acrobat balancing a shifting load. The movements are slow, graceful, and unavoidable. As the atmosphere transfers moisture from oceans to continents and back again, as glaciers expand and retreat, the distribution of mass keeps changing, nudging the axis ever so slightly. The planet, though vast, behaves as delicately as a compass needle finding equilibrium. The implications reach far beyond geophysics. From a geographic perspective, the movement of mass is a story about connections. Meltwater from polar ice can influence not just sea levels, but also the stability of coastal cities. Groundwater depletion in one region can contribute to sea level rise in another. Even rainfall patterns link continents through shifting heat and mass. Local decisions about irrigation, dams, or energy play out on a rotating world where nothing truly stays local. The redistribution of weight through water is one of the few ways humans now influence the physical orientation of the entire planet. For those who study maps, the drifting poles and rebounding crusts are more than curiosities. Precise coordinates, the backbone of navigation and satellite systems, depend on knowing where Earth's centre of mass and rotation axis lie at any given moment. As ice melts and land uplifts, the reference frames that underpin global positioning systems must evolve with them. The coordinates of a mountain summit, a tide gauge, or a deep space antenna shift slightly from year to year. Mapping Earth today is not about pinning down permanence, it's about tracking motion with relentless accuracy. There's a quiet poetry in the way water can steer a planet. Every glacier, every aquifer, every raindrop participates in an unending exchange of mass that keeps the Earth in motion. The solid crust rises and sinks in response, flexing like a memory foam pillow beneath the weight of oceans and ice. The poles trace gentle arcs in the Arctic sky, their direction a silent report on how the world's balance is changing. In the grand scale of time, the story of ice and water is also a story of resilience. Long after today's cities crumble, the crust will still be rebounding from the last great freeze, and the oceans will still be redistributing mass to find equilibrium. The Earth has always moved to the rhythm of its own weight, and now, for the first time, part of that rhythm comes from us. A planet that once adjusted only to glaciers and tides now listens to the pumps, pipes, and reservoirs of its restless inhabitants. And somewhere beneath our feet, that viscoelastic world continues its patient dance, sagging where the ice grows heavy, rising where it melts away, spinning just slightly off-centre as it balances the restless cargo of its water. If you've ever watched a weather map of swirling clouds and wondered whether those movements could possibly matter to something as vast as the whole planet, the answer, surprisingly, is yes. The atmosphere and oceans do more than sculpt weather. They actually push and pull on the solid Earth itself. Every gust of wind, every shifting current, carries angular momentum, and when that momentum changes, the planet responds. The result is a subtle but measurable dance between air, water, and stone, one that can nudge the position of the poles, change the length of the day, and draw looping patterns across the sky that only the most sensitive instruments can see. To picture what's happening, imagine Earth as a single spinning system made up of several interlocking layers. The solid crust and mantle rotate together like a giant gyroscope. Above that lies a fluid shell of atmosphere, and beneath the surface lies an even larger, slower oceanic counterpart. Each layer can move independently, and all share angular momentum, the quantity that keeps a rotating body turning at a steady rate. When air speeds up in one part of the world or ocean currents surge in another, that momentum must come from somewhere. Because total angular momentum is conserved, the solid Earth adjusts in the opposite direction to keep the balance. It's a planetary version of an ice skater extending or retracting their arms, except the skater here is 40 million times heavier and a great deal more graceful. One of the simplest examples lies in the seasonal cycle of winds. During northern hemisphere winter, powerful jet streams strengthen and the atmosphere rotates just a bit faster around the planet's axis. To compensate, the solid Earth slows down fractionally. The length of the day increases by a millisecond or so. When the winds calm in summer, the process reverses. The atmosphere loses angular momentum, the planet spins up again, and days shorten slightly. These changes are invisible to daily life, yet astronomers must correct for them to keep telescopes pointed accurately and satellite orbits precisely timed. A year, it turns out, isn't quite the same length from one season to the next. The same exchange happens horizontally, not just in spin rate but in direction. Winds and ocean currents can shift the distribution of mass around the globe, effectively moving Earth's rotation axis relative to its crust. As atmospheric pressure systems form and migrate, they cause the air column above certain regions to grow heavier or lighter. The planet reacts by adjusting its rotation so that angular momentum remains conserved. This produces a small motion of the poles, a slow, looping drift called polar motion. Over the course of a year, the pole traces an irregular circle a few meters wide, responding to the annual rhythm of the climate. Scientists can actually track these seasonal loops with astonishing precision. By combining satellite data, ground-based observations, and models of air and water circulation, they can see how Earth's spin axis wobbles in near real time. When strong monsoons build over Asia, or large pressure anomalies develop over the Pacific, the loops widen or shift direction. It's as if the atmosphere and oceans are tugging gently on the planet's shoulders, causing it to sway ever so slightly as it turns. A particularly striking example comes from the phenomenon known as El Niño and its counterpart La Niña, the warm and cool phases of a natural oscillation in the tropical Pacific. During El Niño, warm surface waters spread eastward across the ocean, altering wind patterns, rainfall and pressure distributions over half the world. The extra warmth increases atmospheric angular momentum, and the resulting mass shifts are large enough to move the planet's rotation axis by several centimetres. La Niña does the opposite, drawing the pole back toward its previous position. These movements are small on a planetary scale, but entirely real. Instruments in space can detect the changes, and the path of the pole over time carries faint but visible traces of each major El Niño event. Even without El Niño, the constant interplay between air and water never stops. The great ocean gyres, those slow-moving continent-sized spirals of current, store angular momentum in vast quantities. When the trade winds strengthen, they pile water against continental shelves, and the redistribution of mass ever so slightly shifts the planet's balance. Seasonal snow and ice have similar effects. When snow blankets Siberia or Canada, the added weight changes the distribution of mass, and the Earth adjusts by moving its spin axis toward the heavier hemisphere. When that snow melts in spring, the process reverses. Every breath of the climate leaves a trace in the geometry of the planet. For geographers and geophysicists, these connections are more than curiosities. They're essential corrections in the precise science of geodesy, the measurement of Earth's shape, orientation, and gravity field. High-precision satellite systems, whether for mapping, navigation, or studying sea level, depend on knowing exactly how the planet is rotating at any given moment. When atmospheric or oceanic angular momentum changes, the coordinates of ground stations effectively shift by centimetres. The data may be adjusted in real time to keep everything consistent. The result is that every GPS signal, every Earth-observing satellite image, and every precise map quietly carries within it a record of how winds and waters were flowing that day. The physics of these exchanges is elegant and absolute. Angular momentum cannot be created or destroyed, it can only be transferred. The total spin of the entire Earth system stays constant, but the distribution between solid, liquid, and gas changes continually. This is why the phrase, "weather that nudges the world," is more literal than poetic. The trade of momentum between air, sea, and land is continuous, shaping both the fleeting patterns of climate and the enduring geometry of the globe. Because these movements are small, they offer comfort as well as curiosity. The planet isn't lurching under the influence of every storm. The shifts are tiny, measured in millimetres and milliseconds, yet the fact that they can be measured at all speaks to the precision of modern science. In the 19th century, even the existence of such minute wobbles was unimaginable. Today, satellites can detect the effect of a particularly windy winter. The world's most advanced clocks, accurate to a fraction of a billionth of a second, can tell when Earth's rotation speeds up or slows down by barely perceptible margins. From a wider perspective, the exchange of momentum between the atmosphere, the oceans, and the solid Earth is a reminder of how connected everything truly is. A strong Pacific storm may tweak the planet's rotation by a hair's breadth. A season of monsoons may shift the pole's path by a few centimetres. These are not catastrophes, merely whispers in the motion of a planet that keeps exquisite balance despite all its internal motion. The atmosphere rushes, the oceans swirl, and the continents stand firm, yet all three remain part of the same turning whole. In a sense, it's comforting to imagine that the Earth feels its weather, even if only faintly, that each change in wind or current leaves a trace, a soft impression in the dance of its spin. The loops that the pole draws year after year are the signatures of the seasons themselves, written not in ink or on paper, but in geometry and time. And as the world turns, the rhythm continues, air trading motion with stone, sea currents passing it back, a ceaseless and delicate balancing act that holds steady the great spinning sphere we call home. Every so often, the planet gives a sudden, unmistakable reminder that it's alive beneath its quiet surface. A mountain shudders, the ground ripples, and an earthquake releases energy stored for centuries. But even when the shaking stops, something invisible lingers. The entire planet has been nudged ever so slightly, changing the way it spins. The difference is microscopic yet measurable. A few microseconds trimmed from the length of a day, a subtle rebalancing of Earth's figure, and a new alignment of its rotation axis by a few centimetres. These are the hard jolts in the slow ballet of Earth's spin, tiny corrections in a system that never stops seeking balance. At first glance, it seems almost impossible that an earthquake could change the length of a day. After all, how could the movement of a fault line a few hundred kilometres long affect a planet more than 12,000 kilometres across? The answer lies in redistribution of mass. Earthquakes don't just release seismic waves, they shift the position of rocks by tens of metres along faults, rearranging the weight of the crust. Because the planet spins, even a small change in how mass is distributed can alter its moment of inertia, the same physical principle that governs a figure skater spinning faster by pulling in their arms. When a large earthquake pushes dense rock closer to the Earth's centre, the planet becomes ever so slightly more compact, and its spin rate increases. The day shortens, but only by a few millionths of a second. When an earthquake shifts material outward, the opposite happens. The rotation slows and the day lengthens. It's the same energy bookkeeping that occurs when glaciers melt or winds accelerate, except earthquakes perform the adjustment abruptly, in seconds rather than seasons. The effect isn't uniform around the globe. Each quake imparts its own fingerprint depending on where it occurs and in what direction the fault moves. The 2004 Sumatra-Andaman earthquake, one of the most powerful ever recorded, not only unleashed a devastating tsunami, but also shifted the position of the rotation axis by a couple of centimetres. The 2011 Tohoku earthquake off Japan, another enormous event, produced a similar effect, enough to shorten the day by roughly 1.8 microseconds and tilt the figure axis by several centimetres toward the east. These are unimaginably small changes, yet modern instruments can detect them with ease. To understand why, it helps to know that the Earth's shape is not perfectly spherical. The planet bulges at the equator and flattens slightly at the poles because its rotation causes material to spread outward around the middle, a bit like a ball of dough spinning on a baker's palm. The measure of this flattening is known as J2, a parameter that describes how the mass of the planet deviates from a perfect sphere. When something alters the distribution of mass, melting ice caps, shifting oceans, or even a colossal earthquake, J2 changes too. You can think of J2 as a measure of Earth's waistline. A larger J2 means the planet's equatorial bulge is more pronounced, while a smaller J2 means it has become slightly rounder. Earthquakes that move mass toward the poles or the centre tend to reduce that bulge, making the planet a touch more spherical. Over the last few decades, satellites have been tracking J2 with exquisite precision, using measurements of gravity and orbit perturbations. These data reveal not only the long-term effects of melting ice sheets, but also the tiny sudden jumps that follow major seismic events. The world's shape literally twitches when faults rupture. Yet as dramatic as it sounds, the average person will never notice. The difference in day length after even the most powerful quake is far smaller than the blink of an eye, and is dwarfed by the constant variability caused by atmospheric winds and ocean currents. Our clocks, tied to atomic vibrations, tick on undisturbed. Even the tilt of the axis is insignificant from a human perspective. If the pole drifts by 5 centimetres, the corresponding shift on the ground is smaller than the width of your hand. The Earth's wobble may fascinate geophysicists, but it's invisible to everyone else. Still, these minuscule changes carry enormous scientific meaning. They allow researchers to understand how elastic and dynamic our planet truly is. When seismologists and geodesists analyze shifts in rotation and gravity, they gain insight into how the deep interior of the planet behaves, whether the mantle flows more like stiff toffee or soft clay, and how energy travels through its layers. Each earthquake, in a sense, performs a natural experiment, revealing how the Earth flexes under stress. Consider the 1960 Chile earthquake, the most powerful ever recorded, with a magnitude of about 9.5. It caused such a redistribution of mass that scientists estimated the day shortened by about 8 microseconds. Even that colossal event altered only the tiniest details of the planet's rotation. But in its aftermath, researchers noticed something else. The deformation from that quake still reverberates decades later. As the crust continues to adjust and the mantle slowly flows to fill gaps and relieve stress, the gravitational field of the Earth subtly evolves. This lingering relaxation is known as post-seismic deformation, and it shows that the planet takes its time to settle, just as a bell continues to ring after being struck. The beauty of modern geophysics is that it can detect such faint tremors in the planet's behaviour. Satellite laser ranging, very long baseline interferometry, and the GRACE gravity mission all contribute to tracking how Earth's spin responds to seismic jolts. When a massive earthquake occurs, scientists watch for changes in both the length of day and the value of J2. Even if the adjustments are minute, they confirm that our models of the planet's interior and its moment of inertia are on the right track. It's worth pausing on the contrast between the violence we feel at the surface and the serenity of the global effect. For the people living near a fault, an earthquake can be terrifying, a brutal rupture of the ground that destroys homes and lives in seconds. Yet for the planet as a whole, that same event is merely a whisper, a flicker of motion in a vast and ancient equilibrium. the Earth absorbs the shock, redistributes its weight, and continues spinning with hardly a pause. The scales of experience could not be more different. Chaos for the human observer, calm adjustment for the globe. There's something quietly reassuring in that. Despite all the shaking, the Earth remains steadfast in its rotation. The quakes come and go, the crust rearranges itself, and the planet continually finds its balance anew. Even the strongest jolts remind us of the delicate interplay between chaos and stability. The same physics that causes buildings to sway also keeps the world spinning at a pace that defines our seconds and hours. Next time you hear of a major earthquake on the news, consider that somewhere, buried deep in the data streams from satellites and observatories, the planet's spin will show a faint blip. A record of the moment when rocks miles beneath the surface shifted and Earth subtly reshaped itself. The difference won't affect your clock, your compass, or your day. But it's a quiet testament to a living planet, one that never stops adjusting its balance, even after the ground falls silent. For all our obsession with precision, the length of a day on Earth is not constant. It stretches and contracts by fractions of a millisecond, flexing like the planet's own slow heartbeat. To most people, these variations are invisible, but to the keepers of time, astronomers, navigators, and geodesists, they're a daily reminder that our hours are carved out of motion, not machinery. Every sunrise, every tick of the clock depends on how steadily our planet spins, and the truth is, it's never perfectly steady. The story begins billions of years ago, when the Earth and the Moon were still finding their rhythm. Back then, the Moon orbited closer, the tides rose higher, and the planet spun faster. Each day was perhaps only 6 hours long. But the pull of those enormous tides acted as a brake. As the ocean bulged and lagged slightly behind the Moon's orbit, it dragged against the seafloor, converting rotational energy into heat. That friction slowed Earth's spin, even as it flung the Moon farther away. Over time, the partnership between planet and satellite has settled into a long, quiet negotiation. The Moon drifts outward by about 4 centimetres each year, and the Earth's day lengthens by a few milliseconds per century. Tidal friction is one of the most delicate yet persistent sculptors of time. Of course, the tides aren't alone in tugging on the planet's rhythm. Deep inside the Earth, the molten outer core and the solid mantle rotate at slightly different speeds, coupling and decoupling like gears that never quite align. Magnetic forces transfer angular momentum between these layers, adding to the small, irregular changes in rotation rate. Then there are the surface factors, shifting winds, melting glaciers, atmospheric pressure changes, all of which redistribute mass and subtly adjust the planet's spin. Some of these effects lengthen the day, others shorten it. On average, they nearly cancel out, but not perfectly. So the length of a day, measured precisely, never stays exactly 24 hours. This poses an interesting challenge for anyone who needs to keep time consistently. Astronomers define a quantity called UT1, short for Universal Time 1, which tracks Earth's actual rotation, the true physical turning of the planet relative to the sun and stars. It's wonderfully natural but also wonderfully inconvenient because it wobbles unpredictably. To maintain order in our daily lives, we use another standard called UTC, Coordinated Universal Time, which is based on atomic clocks. These clocks are masterpieces of stability. They measure time by counting vibrations of atoms, specifically the frequency of microwave radiation emitted by cesium. They're so precise that they drift by less than a billionth of a second per day. But that's precisely the problem. The Earth itself doesn't match their perfection. As the planet's rotation slows and speeds up, UT1 and UTC gradually drift apart. If left unchecked, noon on your clock and noon in the sky would slowly fall out of sync. After a few centuries, midday might arrive in darkness. To prevent that, the world's timekeepers occasionally perform a strange ritual. They add or subtract a leap second. It's like adjusting the world's largest grandfather clock by slipping in an extra tick, ensuring that atomic time never strays more than 1 second from Earth's natural rhythm. Leap seconds are wonderfully human, a little messy, a little arbitrary, and entirely necessary. Since their introduction in 1972, they've been added 27 times, almost always to slow our clocks down as the planet's rotation lags. For one peculiar moment, a minute lasts 61 seconds instead of 60. Software engineers dread it. Timekeepers cherish it. Each addition is a reminder that our most exacting technology still bows to a spinning rock. The concept sounds simple, but the execution can be surprisingly awkward. Computer systems, for instance, are not fond of unexpected seconds. Some treat them as duplicates, others ignore them altogether. On leap second nights, data centers prepare carefully, international servers hold their breath, and global networks perform synchronized updates to avoid chaos. It's a little ironic that while we can coordinate GPS satellites to the millimetre, the humble task of adding a single second sometimes causes confusion across the digital world. Despite these inconveniences, the distinction between atomic and rotational time has profound importance beyond clocks and computers. It anchors our entire coordinate system. Every longitude and latitude, every point on a map depends on knowing exactly how the Earth is oriented in space at a given moment. If the rotation rate drifts, so do the coordinates. UT1 provides that orientation. It defines where noon and midnight fall on the globe, where the Greenwich meridian lies relative to the sun. When mapmakers, navigators, and space agencies use satellites to pinpoint a location, they rely on models that link geographic coordinates to UT1. Without that alignment, maps would slowly twist out of sync with the planet they describe. There's a pleasing symmetry in this. Time defines geography, and geography defines time. The zero meridian in Greenwich, once marked by telescopes watching stars cross the sky, is both a spatial and temporal anchor. When we say it's midnight UTC, we mean that the sun is directly below the meridian at Greenwich. Every map, every GPS coordinate, every global schedule quietly inherits that geometry. The heartbeat of Earth's rotation, measured through UT1, is the pulse that keeps our maps alive. But as with all living systems, it's an irregular pulse. Sometimes the planet speeds up unexpectedly, shaving microseconds from the day. Scientists suspect that changes in core dynamics or polar winds might be to blame. Other times it slows down, lengthening days just enough to require another leap second. In the early 21st century, something curious happened. Instead of slowing, the planet briefly started spinning faster. Days became a few milliseconds shorter than 24 hours, the fastest recorded since precise measurements began. There was even talk that a negative leap second might eventually be needed, effectively removing a second from the clock. The idea was quietly alarming to timekeepers who had spent decades only ever adding time. It never came to pass, but it showed how dynamic the Earth remains beneath our neatly ticking clocks. At its heart, the dance between UT1 and UTC is a beautiful compromise between nature and precision. UT1 follows the organic rhythm of the planet, tidal drag, shifting air, molten iron, while UTC represents human perfectionism, the desire for order in an untidy universe. The leap second is where the two meet, shaking hands once in a while to stay in step. It's almost funny, really. We've built machines so consistent that they embarrass the planet itself, and yet the Earth keeps reminding us who's in charge. Time, in its truest form, still belongs to the rotation of the world beneath our feet. The rest is just our attempt to keep up, So, next time you glance at a clock and see the seconds marching by with metronomic confidence, remember that they're marching to a tune the Earth can't quite keep. Beneath those steady ticks lies a planet, spins and wobbles, sighs and swells, sometimes gaining a fraction of a breath, sometimes losing one. And somewhere, deep in an observatory or a satellite control room, someone is watching the difference between UT1 and UTC grow by a few thousandths of a second, waiting for the day they'll need to slip another tick into the fabric of time, just to remind the universe that perfection and motion rarely agree for long. When you look at a map, it feels like a promise of stability. Mountains stay where they are, coastlines trace familiar outlines, and cities occupy their steady coordinates. But beneath that comforting certainty is a quiet truth. The Earth is constantly on the move. Continents drift, the crust flexes, and even the poles wander. Every coordinate we use, every latitude and longitude, every measured point on the ground, belongs not to a static planet but to a living, shifting one. To keep our maps honest, we must anchor them to something more than ink and pixels. We need reference frames, invisible scaffolds that hold the planet still long enough for us to measure it. A reference frame, in essence, is a mathematical model of the Earth's size, shape, and orientation. It tells us how to describe a position on a surface that refuses to stay put. There are many ways to define such a frame, but they all share a common goal: to give every point on Earth, from mountain tops to sea floors, a unique and consistent address. The most widely used frame today is WGS84, short for the World Geodetic System, 1984. It underpins the entire GPS network. When your phone tells you where you are, it's referencing your position relative to this model of Earth. But here's the catch: even the best reference frame ages. Because tectonic plates shift by a few centimetres each year, coordinates that were perfectly accurate in 1984 are no longer quite right today. A point in Australia, for instance, has drifted nearly 2 metres northward since the first WGS84 coordinates were published. That's enough to throw off high-precision mapping, survey work, or even autonomous navigation. Maps, like milk, have expiry dates. They grow stale unless periodically refreshed. That's where epochs come in. Each official version of a reference frame is tied to a specific moment in time, called an epoch. The coordinates are correct for that instant, say January 1st, 2010, but as plates move, they slowly drift away from their nominal positions. It's like taking a snapshot of a dancer in motion. The image is true for that moment only. To make sure everyone is using the same version of reality, geodesists periodically update the frame to a new epoch, resetting the coordinates to reflect current positions. The International Terrestrial Reference Frame, or ITRF, takes this even further. Instead of freezing the planet in one moment, it continuously models motion. It's the global gold standard of positioning, built from a vast network of GPS receivers, laser ranging systems, and radio telescopes that monitor Earth's shape and spin. The ITRF not only gives coordinates for every observing station, but also describes how each one moves over time, its velocity vector. In other words, every location on Earth's crust is assigned both a position and a speed, as though each point carries a built-in arrow showing where it's heading. Explaining it in simpler terms, think of a map that knows not only where you are, but also how fast your part of the planet is drifting. That's essentially what the ITRF provides. North America slides westward, Eurasia shuffles east, Australia races north toward Asia at about 7 centimetres a year. None of these motions are dramatic to the naked eye, but they matter profoundly when your instruments can measure distances to millimetres. Different applications demand different levels of precision. For everyday GPS, your phone finding a cafe, your car navigating a road, these tectonic shifts are negligible, but for surveyors marking property lines, for engineers aligning bridge spans, or for scientists measuring sea level change, a few centimetres can mean everything. Infrastructure that relies on geospatial data, from pipelines to runways to satellite networks, needs coordinates that match reality as closely as possible. A bridge built using outdated coordinates might appear misaligned in modern maps. A pipeline could seem to wander across boundaries that have shifted only in the mathematical sense. Australia offers a neat example of this challenge. Because the continent sits on a fast-moving plate, its coordinates in the global WG84 frame drift steadily northward. To fix this, Australia's geodesists periodically jump the national datum, the reference surface used for mapping, back into place. In 2017, they shifted the country's coordinates by about 1.8 metres to match where the land actually sits relative to the GPS satellites. Without that adjustment, a self-driving car navigating by global coordinates would think it was several lanes away from reality. All of this may sound wonderfully abstract, but it has tangible consequences. Survey control points, the brass discs or steel bolts set into the ground to mark official reference positions, depend on being tied to a specific frame and epoch. When the frame updates, those points effectively move, even though the ground beneath them hasn't changed. Surveyors must account for this drift to ensure consistency. It's one reason why geodesy and geography are forever linked. Mapping isn't just about drawing landscapes, it's about tracking their motion through time. These global models rely on extraordinary international cooperation. Agencies across continents contribute data from thousands of monitoring stations, satellites, and observatories. The ITRF blends all of these inputs into a unified, precise framework that accounts for everything from tectonic motion to glacial rebound. It even includes corrections for the Chandler wobble and variations in Earth's rotation, those subtle effects that, though small, can accumulate over time. What results is a reference frame so stable that its uncertainty is measured in millimetres, yet flexible enough to evolve as the planet does. To make things manageable, scientists also define plate-fixed frames, versions of the global model that hold a particular tectonic plate still. WG84, for instance, is tied closely to the motion of the North American plate. That makes it ideal for GPS users in that region, but less perfect for continents that drift in different directions. Other regional datums, like Europe's ETRF or Australia's GDA, are designed to remain stable for their respective plates, giving local users coordinates that don't slowly creep year by year. It's a bit like having both a global map of ocean currents and a local tide chart. You need both to navigate accurately. From a geographer's perspective, the beauty of these systems lies in their humility. They acknowledge that fixed is an illusion. The ground beneath us is not fixed at all, and our coordinates are only as true as our models of motion. Reference frames are the quiet translators between a restless Earth and the human need for stable reference. They tell us where here is, not just today, but tomorrow and 10 years from now, provided we remember to keep updating them. In a way, this constant recalibration is comforting. It shows that our planet's dynamism is not chaos but rhythm, a slow drift we can measure, predict, and adapt to. Every GPS fix, every survey mark, every digital map is part of an ongoing dialogue between science and geography, between motion and measurement. The next time your phone locks onto satellites and tells you exactly where you're standing, take a moment to appreciate what that really means. You're not just pinpointed on a static globe, you're located on a planet that's sliding, wobbling, and breathing through space. And yet, thanks to a lattice of invisible mathematics called the ITRF and WGS84, you still have an address. It's a small miracle of modern mapping. A moving Earth, held still just long enough to find your way home. If you've ever held a compass and watched its needle twitch, you've witnessed one of geography's quiet quirks, the uneasy relationship between true north and magnetic north. They sound like twins, but they live slightly apart. True north is the direction of the geographic pole, the axis around which the Earth spins. Magnetic north, meanwhile, is the point where the planet's magnetic field dips vertically into the surface. Compasses are faithful to magnetism, not geometry, and that small distinction means that the direction they indicate is never quite fixed. At the moment, the magnetic North Pole sits somewhere in the Arctic Ocean, north of Canada, but it's been steadily migrating towards Siberia at a rate of more than 50 kilometers per year, faster than at any other time in recorded history. This drift means that every map, every navigation chart and every compass correction must occasionally be adjusted. The angle between magnetic north and true north is called declination, and it changes depending on where you are on Earth. In London, for instance, magnetic north now lies slightly east of true north, but only a few years ago it was west. In parts of Alaska, the two norths are separated by more than 20 degrees. For hikers and navigators, these subtle differences matter. Following a compass bearing without accounting for declination can lead you kilometers off course on long routes. That's why good maps include a small diagram showing the difference between magnetic and true north, and how quickly that difference is changing. Most national mapping agencies publish updated magnetic declination information every few years, allowing explorers and surveyors to recalibrate their sense of direction. It's a lovely reminder that even something as simple as north is a living, moving concept. In aviation, the difference plays out on a grander scale. Runways around the world are numbered according to their magnetic heading, the direction a plane's nose points, rounded to the nearest 10 degrees. A runway aligned toward magnetic north might be called 01 for 10 degrees at one end and 19 for 190 degrees at the other. But because the magnetic pole is drifting, those headings slowly change. When the difference becomes large enough, typically around 5 degrees, airports have to renumber their runways. It's not just a matter of repainting numbers. Signs, charts and navigation databases must all be updated, sometimes at enormous cost. In 2009, for example, Tampa International Airport in Florida renumbered all 3 of its runways because magnetic north had shifted far enough to make the old headings misleading. In the Arctic, where declination changes quickly, runways may need renumbering more than once in a generation. Pilots depend on magnetic bearings because magnetic compasses remain one of the simplest, most reliable instruments on board. But for long-distance navigation, especially over oceans, they also use true north, calculated from gyroscopic or satellite systems that rely on Earth's rotation rather than its magnetic field. That distinction between magnetic and true bearings lies at the heart of modern navigation. True north provides stability. It doesn't wander across the planet, and it's defined by something immutable, the Earth's spin axis. Satellite navigation systems such as GPS rely on it to fix coordinates that remain valid regardless of local magnetic quirks. Magnetic north, in contrast, offers immediacy. It's accessible to anyone with a compass, no satellites or batteries required. Together they form a partnership of resilience, the global, unchanging frame of true north, complemented by the personal tactile guidance of magnetism. Interestingly, as our technology becomes ever more sophisticated, the oldest form of navigation is quietly making a comeback. Celestial navigation, the art of finding one's position using the sun, moon, planets, and stars, is being reintroduced in some areas of aviation and maritime training as a backup for satellite systems. In 2016, the United States Navy reinstated celestial navigation lessons after a long hiatus, acknowledging that while GPS is extraordinarily accurate, it is also vulnerable to interference and failure. The stars, by contrast, are timeless and immune to power outages. Celestial navigation is both science and poetry. It uses the predictable geometry of the heavens to determine where you are on Earth. The North Star, Polaris, sits less than a degree from the true celestial pole, making it an enduring guide to true north for observers in the Northern Hemisphere. The angle between Polaris and the horizon reveals your latitude. With a sextant and a clock, a navigator can plot a position anywhere on the planet. In a world of digital maps and instant directions, the thought of charting a course by starlight feels almost romantic. But it also reminds us that every modern coordinate still depends on celestial mechanics. The coexistence of these systems, magnetic, true and celestial, creates a layered geography of direction. Pilots, sailors, surveyors, and even hikers move seamlessly between them, sometimes without realizing. The compass points toward a restless magnetic pole, the GPS points toward a mathematical axis, and the night sky points toward eternity. Every journey is a blend of all three, anchored by technology but still guided by the same cosmic geometry that led ancient explorers across oceans. For those who spend time outdoors or work with maps, a few simple habits can help make sense of this shifting world. First, always check the date on your map. If it's more than a decade old, its magnetic declination might already be out of date. Modern maps often include annual rates of change so you can adjust accordingly. Second, learn the local declination before you set out, and practice converting between magnetic and true bearings. It's as easy as adding or subtracting a few degrees, but it can save you from wandering miles in the wrong direction. And third, whenever possible, use natural cues, the sun's arc, the stars, even the shape of vegetation, to confirm what your instruments tell you. The best navigators trust both data and instinct. Understanding these distinctions also adds a quiet pleasure to the act of navigation. There's something grounding about realizing that the direction your compass shows is not the same one the stars insist upon, and that both are valid depending on your purpose. The magnetic field, generated deep within the molten outer core, hums with the planet's inner life. True north, fixed by the rotation axis, reflects the stately precision of celestial mechanics. Between them lies the human realm, where we draw lines on maps and decide which version of north suits the job at hand. Despite all this complexity, everyday navigation remains remarkably reliable. Modern instruments constantly update to account for pole drift, and GPS ensures that the coordinates of airports, ports, and highways remain aligned with reality. Even the runways that must occasionally change numbers remain physically the same. Only our labels move to match the planet's shifting magnetism. In the end, the world's directions are less like rigid arrows and more like gentle currents. They drift and adjust, yet always lead us home. Whether guided by a compass needle, a satellite constellation, or a single steadfast star, we navigate through a moving world with tools that adapt as gracefully as the planet itself. And perhaps that's the real marvel. In a universe where even north refuses to stay still, we've learned to find our way by embracing the motion, not resisting it. When people imagine the poles, they often picture them as abstract points on a globe, clean, geometric, and perfectly defined. Yet in reality, the North and South poles are not dots you can truly stand on. They're environments, vast and restless, layered with history, science, and silence. They are the ends of the Earth not just in space but in feeling, places where geography, climate, and human endurance meet at the very limit of what is possible. The Arctic and Antarctic could not be more different. The Arctic is an ocean surrounded by continents, its heart covered by floating sea ice that waxes and wanes with the seasons. The Antarctic, by contrast, is a continent encased in ice, surrounded by ocean and battered by the world's fiercest winds. One is a frozen sea dotted with drifting floes and migrating animals. The other is a frozen land, stark and mountainous, almost entirely lifeless inland. Yet both are bound by the same geometry of sunlight, months of unbroken day followed by months of darkness, and a constant delicate balance between solid and liquid, motion and stillness. At the North Pole there is no permanent land at all. The ice beneath your boots is a floating sheet, shifting with the Arctic currents. If you were to plant a flag at the exact coordinates of 90 degrees north, it would begin to drift almost immediately, carrying you away from the top of the world without your noticing. Explorers have learned this the hard way. Even when early expeditions believed they'd reached the pole, the ice moved beneath them, blurring certainty. Today, the drifting nature of the Arctic remains central to science. Research stations like Russia's historic North Pole series or modern international projects are built on these transient platforms, small cities of tents and instruments that drift hundreds of kilometres over the months, recording data on sea ice, ocean chemistry, and the upper atmosphere. This mobility gives the Arctic a sense of impermanence that defines life there. The sea ice itself breathes with the seasons, expanding in winter until it nearly bridges continents, then retreating in summer to reveal dark water. The people who live around the Arctic Rim, the Inuit, Sami, Chukchi and others, understand this fluid geography intimately. Their traditional knowledge reflects a world where maps are less about fixed coordinates and more about shifting patterns of ice, weather, and animal migration. For them, direction is found in memory, sound, and instinct as much as in north or south. The South Pole, by contrast, sits atop solid ground, or at least ground buried under nearly 3 kilometres of ancient ice. Here, the air is so dry it squeaks beneath your boots, and the temperature rarely rises above -20 degrees even in summer. It's a place where the concept of south dissolves. Every direction you face points north. Yet even this seemingly immovable location is not perfectly still. The Antarctic ice sheet is slowly flowing outward from the continent's centre, carrying the Amundsen-Scott South Pole Station with it at a rate of about 10 metres per year. To mark the true pole's wandering, a new ceremonial marker is installed every New Year's Day, a beautifully crafted symbol of human persistence amid constant motion. The old marker remains behind, forming a quiet trail across the snow, a dotted line of years leading into the white distance. Logistics in these regions are a kind of choreography against chaos. Everything must be planned months ahead and executed with precision, yet the environment is always rewriting the script. Supply flights to Antarctica depend on windows of calm weather and the careful management of ice runways that melt and refreeze with the season. In the Arctic, sea ice can crush ships that linger too long, yet it can also carry drifting research camps across hidden territories, turning chance into discovery. Scientists at both poles live within a delicate rhythm of waiting, for clear skies, for daylight, for cargo, for rescue. In a world obsessed with speed, the polar regions force humanity to move at the pace of the planet. Despite the harshness, there's an almost meditative quality to life at the extremes. The landscape feels infinite yet intimate, reduced to essential contrasts: ice and sky, light and shadow, silence and wind. In the high Antarctic interior, the stillness can be so complete that you hear your own heartbeat. The absence of sound becomes its own presence, a vast unbroken hush that reminds you how small you are in the scale of things. Even in the Arctic, where the wind is more talkative and the sea ice groans like an old wooden ship, there are moments of profound quiet, when snowflakes drift soundlessly through pale air and time itself seems to pause. These are not empty spaces. The Arctic hosts communities, traditions, and ecosystems of astonishing resilience. Narwhals threading through leads in the ice, polar bears ranging across floes, mosses and lichens clinging to gravel under a midnight sun. The Antarctic, though devoid of permanent residents, teems with life at its edges. Penguin colonies, seals, krill and seabirds, sustained by the nutrient-rich waters of the Southern Ocean. Both regions are laboratories of adaptation, where everything that survives has learned patience. For geographers and scientists, the poles are also living laboratories of motion. Sea ice drift reveals ocean currents. The movement of glaciers tells of climate and gravity. GPS beacons trace how the ice sheets deform under their own weight. The data are intensely practical, crucial for understanding climate change, sea level rise, and planetary dynamics, but they also have a strange poetry to them. Each instrument left in the snow continues to whisper coordinates into the cold air, marking the slow rearrangement of Earth's mass, as if the planet itself were writing a diary in numbers. Small positional shifts, whether from drifting ice or from the slow migration of the rotational axis, are simply folded into the rhythm of polar logistics. No one worries that the ceremonial South Pole marker moves a few centimetres each month, or that a drifting station ends a season hundreds of kilometres from where it began. Precision here is relative. What matters more is the continuity of presence, the ongoing observation of a changing planet. In this way, even the act of staying put becomes an act of navigation. There is a peculiar serenity in seeing these extremes not as edges but as centres, places where the geometry of Earth converges and where human curiosity meets the natural limits of endurance. The poles remind us that geography is not just about location, but about relationship. How we orient ourselves to a world that refuses to stay still. Stand for a moment in your imagination at either pole. Above you the sky spins in a perfect circle, tracing the slow pivot of the world. Beneath you the planet turns with quiet determination. Around you stretches a horizon of pure distance, where light never quite fades. It's a landscape of silence, yes, but also of wonder, the kind of silence that listens back. Every culture has looked up at the night sky and found not just stars but stories. Where modern maps see coordinates, ancient eyes saw pathways. For most of human history, direction was not something fixed on paper or displayed on a glowing screen. It was something felt in the body, sung in memory, and traced through the movement of the heavens. The idea of north or south has always been more than geometry. It has been spiritual, practical, and deeply human. In many traditions, the directions themselves were alive, sacred points in a circle connecting people to land and sky. Among several indigenous nations of North America, the cardinal directions are woven into ceremony and cosmology: east for beginnings, south for warmth, west for endings, north for wisdom and endurance. In the Arctic, Inuit hunters speak of orientation not as a matter of compass points, but of relationships to the wind, the sea, the drift of ice. In desert Australia, many Aboriginal cultures describe their worlds through songlines, invisible trails connecting sacred sites whose verses encode direction, waterholes, and even the shapes of constellations. These aren't maps in the Western sense, they are living geographies sung into existence with each journey. The pole star, a symbol of steadfastness in many cultures, has not always occupied its familiar place. Today, we look up to Polaris as the bright sentinel marking the northern axis of the world, but that is only true for a few thousand years, because Earth's axis slowly precesses, completing a great circle every 26,000 years. The celestial pole drifts through the sky. Long ago, the star Thuban in the constellation Draco held the title of North Star. In about 12,000 years' time, Vega in Lyra will take its place. To those who watched patiently across generations, Even the heavens seemed to breathe. Yet people have always adapted. Long before magnetic compasses, sailors, herders, and travellers learned to read this moving sky as naturally as one reads a familiar face. The Polynesian navigators of the Pacific, for instance, mastered the art of wayfinding without maps or instruments. They memorized hundreds of stars and their rising and setting points, using them as a kind of celestial lattice to steer by night. By day, they read the pattern of ocean swells, the colour of the sea, the flight paths of birds, and the faint reflections of islands on the underside of clouds. The sea itself became a map that moved with them. Their knowledge was carried not in charts, but in stories, chants, and training that could take years to master. The star compass of Polynesian voyagers remains one of the most extraordinary achievements in human navigation, a geometry written in wind and wave. In the Northern Hemisphere, other cultures found their own celestial guides. The ancient Egyptians aligned their pyramids with remarkable precision by observing circumpolar stars, those that never set, believing them to represent eternity. In China, the north was the direction of the celestial emperor, symbolized by the purple forbidden enclosure, a cluster of stars near the pole. The axis of the world was seen as a cosmic pivot linking heaven and earth. Farther south, in sub-Saharan Africa and the islands of the Indian Ocean, navigators worked without a fixed polar star, relying instead on patterns that circled low on the horizon or on the rising points of constellations. Each region developed its own north, tied to local ski and land. For the peoples of the southern hemisphere, the story unfolds differently. There is no bright pole star to mark the axis. Instead, the Southern Cross, or crux, serves as a signpost. Its long axis points toward the celestial South Pole, a direction marked not by a single star but by an invisible idea. In Australia, the Southern Cross features prominently in dreaming stories, representing ancestral beings, canoes, or spiritual guardians depending on the community. In New Zealand, Maori navigators saw the same constellation as Te Punga, the anchor of a celestial canoe. Across the Pacific and the southern continents, these stars are not abstract dots but family, companions for those who travel the long distances between islands and generations. In a sense, the movement of the poles through time has always been reflected in myth. As the celestial axis drifts, so too do the stories attached to it. Some northern cultures spoke of a cosmic tree whose roots and branches connected the world below with the heavens above, its trunk aligned with the north pole of the sky. The Sami people of northern Europe imagined the sky as a vast dome supported by this world tree, at whose apex burned the pole star. In ancient Mesopotamia, the heavens revolved around a fixed star that anchored creation. These were ways of giving motion meaning, of turning cosmic drift into narrative stability. What's striking is how consistent the human impulse is, even across vast differences of place. From the Arctic tundra to the Pacific atolls, from the steppes of Mongolia to the Andes, people have always sought orientation not just in space, but in story. The sky becomes a kind of mirror, reflecting the order, values and relationships of the culture that gazes upon it. To navigate in these traditions is to belong. Modern navigation, though it trades in satellites and signals, still carries echoes of this older wisdom. The global positioning system depends on stars of a different kind, machines in orbit that broadcast precise timing data. But the principle is the same, position derived from the dance of celestial bodies. Even the constellations of satellites are arranged with respect to Earth's axis and its slow wobble. We have not abandoned the stars, we have mechanized them. There is a gentle irony here. For all our technological sophistication, we still correct our instruments by looking to the heavens. Astronomers align telescopes using reference stars. Navigators check inertial systems against the sun. Every time we adjust a satellite's clock, we are compensating for the same gravitational and rotational quirks that ancient stargazers once embodied in myth. The language has changed, but the relationship between human curiosity and cosmic rhythm remains the same. To see the night sky this way is to understand geography as something larger than terrain. It's not only about land and water, but about the patterns of the universe that shape our sense of direction and meaning. Indigenous navigators remind us that knowledge is relational, not mechanical. It flows from deep attention, repetition, and respect for the environment. A star is not just a point of light, it is a teacher, a coordinate, and a companion. Perhaps that's why the concept of north still carries such symbolic weight. Even as the magnetic pole sprints across the Arctic and the celestial pole drifts among constellations, we continue to treat north as a metaphor for steadiness, the arrow on every compass, the anchor on every map. Yet the deeper truth, known intuitively to the world's oldest navigators, is that stability is an illusion. The poles move, the stars change, and our task is not to freeze them in place but to keep following with grace. Look up on a clear night far from city lights, and you'll see what generations before you saw, a sky in slow motion. The stars slide imperceptibly, tracing the great circles of time. Somewhere above you, the true pole marks the axis of that motion, invisible but real, the quiet hinge of our spinning world. Around it turn the stories of every people who ever sought their way by starlight, each one finding their own north and carrying it home. The ground beneath your feet is a vast archive, written not in ink but in magnetism, minerals, and ice. Every layer of rock, every grain of sediment, every trapped bubble of ancient air holds a memory of where the poles once were and what the planet once felt like. These clues let scientists reconstruct the geography of worlds that vanished millions of years ago, Earths with different coastlines, different climates, and even different notions of north. To study them is to realize that our world is not a fixed stage, but a story in motion, constantly rewriting itself with quiet persistence. One of the most remarkable storytellers in this archive is paleomagnetism, the study of how rocks record the direction and intensity of Earth's magnetic field at the time they formed. When molten rock cools, or when fine sediments settle in calm water, magnetic minerals within them align with the planet's magnetic field, pointing toward the ancient magnetic north. Once locked in place, they preserve that direction for millions of years, even if the rock later moves across the planet. By measuring the magnetic orientation of rocks of different ages on different continents, scientists can trace how those continents have drifted and rotated through time. It's like comparing snapshots in an album that spans geological ages. A basalt flow in India might reveal that 65 million years ago, the subcontinent lay far south of the equator, speeding northward toward Asia. A sandstone in North America might show that the continent once tilted differently, its ancient pole located thousands of kilometers away from today's. These findings allow geologists to piece together the puzzle of continental drift, transforming static maps into dynamic films of shifting plates. The pattern of those ancient poles, as called paleopoles, is crucial for understanding how the planet's magnetic field and geography have evolved together. They reveal that the magnetic poles have wandered across the globe countless times, tracing graceful arcs that correspond to the movements of continents. When plotted on a world map, these arcs are known as apparent polar wanderpaths, and comparing them from one continent to another helps scientists determine when land masses were joined or apart. It's one of the quiet triumphs of Earth science, using the whisper of magnetized minerals to reconstruct continents that no longer exist. But magnetism is only part of the story. Sediments and ice tell their own tales of ancient worlds. Layers of mud and sand deposited in lakes and oceans hold microfossils, chemical signatures, and traces of past climates. Each layer corresponds to a slice of time, perhaps a few decades, perhaps thousands of years, preserving how temperature, salinity, and vegetation changed. By drilling deep into these sediments, scientists can reconstruct the migration of deserts, the spread of forests, and the pulse of ice ages. Further south and north, ice cores extracted from Greenland and Antarctica act as frozen chronicles of the atmosphere. Tiny bubbles trapped within them contain samples of ancient air, the literal breath of past climates. Some cores stretch back more than 800,000 years, revealing cycles of warmth and cold, of carbon dioxide rising and falling like a planetary tide. The delicate layering in these cores shows how volcanic eruptions, solar fluctuations, and orbital variations have all shaped Earth's climate over time. Reading an ice core is like turning the pages of a long, slow diary, written in frost instead of words. These techniques combined to paint extraordinary portraits of past geographies. There were times when the Sahara Desert was lush with lakes and grasses, when Antarctica was covered in forests, when the Arctic Ocean was warm enough for crocodiles. The continents we know today once fit together into supercontinents, Pangaea, Gondwana, Rodinia, and then drifted apart again, like slow-moving rafts on a molten sea. By mapping where the ancient poles lay, geologists can estimate how each landmass was oriented, which way rivers flowed, and where sunlight and monsoons once fell. From these reconstructions emerge not only pictures of the past, but also insights into our future. The same forces that shaped those vanished worlds, the tilt of Earth's axis, the position of the continents, the ebb and flow of carbon, continue to operate today. When scientists use paleogeographic data to build climate models, they are in a sense calibrating the future against the past. The patterns of ancient warmth and cold revealed in rocks and ice show how sensitive Earth's climate is to changes in sunlight and greenhouse gases. The more precisely we understand how the planet has responded before, the better we can predict how it might respond again. For instance, the mid-Pliocene epoch, about 3 million years ago, saw carbon dioxide levels similar to today's, and sea levels were more than 20 meters higher. Reconstructing that ancient geography, the position of coastlines, the extent of ice sheets, the distribution of vegetation, helps scientists refine their projections for modern sea level rise. In this way, paleomagnetism and paleoclimate are not just exercises in curiosity. They are tools for risk assessment, for seeing where future shorelines might fall and where new deserts might grow. There's something soothing about this long view of time. When you hold a rock and realize it carries the direction of a pole that no longer exists, or when you look at a map showing continents gliding across eons, you sense the planet's vast patience. Earth has reinvented itself many times, freezing over, thawing out, gathering continents and scattering them again. Ice has come and gone, seas have risen and fallen, forests have marched across latitudes and vanished into stone. Compared to that slow choreography, our brief centuries of change are only a flicker, though a powerful one. And yet within that flicker we can hear echoes of earlier worlds. The melting of glaciers today mirrors the post-glacial rebounds that lifted Scandinavia after the last ice age. The migration of deserts and shifting of rain belts trace patterns that have played out countless times before. The Earth's crust, mantle, and magnetic field continue their unhurried cycles, adjusting to forces deep within and far beyond. The planet is restless, yes, but also rhythmic, breathing in ice ages, exhaling warm periods, always finding balance anew. The work of reconstructing ancient poles and places is, in the end, an act of humility. It reminds us that our world is not static, nor ours to command. The landscapes we know are temporary arrangements sculpted by time and physics, soon to be reimagined again. But that is not a cause for despair. It's a reassurance that change is the planet's natural language, and that by learning to read it, we can find steadiness within the motion. So when you next stand on a familiar shore or look out across a mountain range, imagine what lies beneath that view. A memory of forests where there is now tundra, seas where there is now desert, and magnetic norths long gone. The earth you stand upon has turned itself inside out many times. It will do so again, patiently, beautifully, without hurry. It has always breathed and shifted, and somehow that gentle continuity makes the movement feel like home. Every few years, headlines resurface predicting an imminent pole shift, the idea that the entire planet might suddenly flip over, sending continents sliding into the sea and rewriting the world's geography overnight. It's an image that captures the imagination. Compasses spinning madly, volcanoes erupting in chorus, and civilization scrambling to hold on as Earth turns itself inside out. But in reality, this is one of those stories where the truth is both calmer and far more fascinating. The poles do move, yes, sometimes dramatically, sometimes gently, but never in the catastrophic, cinematic way those myths suggest. The real motions are governed by physics, not prophecy, and they tell a quieter, richer story about how a living planet keeps its balance. To begin with, it's important to separate two very different kinds of pole shifts. There are magnetic reversals, which involve the flipping of Earth's magnetic field, and geographic or rotational changes, which concern the physical orientation of the planet itself. The two are often tangled together in popular imagination, but they happen in completely different ways and on vastly different timescales. A magnetic reversal occurs when the north and south magnetic poles gradually swap places. The process is driven by the turbulent flow of molten iron in Earth's outer core, where the magnetic field is generated. These reversals are not rare in geological history. They've happened hundreds of times over the past few 100 million years. The last full reversal, called the Brunhes-Matuyama reversal, occurred about 780,000 years ago. The magnetic field weakened, shifted, and eventually reoriented so that compasses that once pointed north would have pointed south instead. What's fascinating is how slow and non-disruptive the process actually is. A reversal unfolds over thousands of years. The field doesn't vanish. It becomes more complex, sprouting multiple poles and weaker regions before stabilizing again. There's no evidence that these events cause mass extinctions or global chaos. Birds and turtles, which use magnetic cues for migration, likely adjust gradually. Humanity, if it had existed during such a transition, might not even have noticed beyond the inconvenience of needing to repaint the N and S on compasses. Yet the idea of a magnetic apocalypse persists. The notion that a reversal would strip away our atmosphere or destroy electrical systems. In truth, while a weakened magnetic field would slightly increase radiation at the surface, Earth's thick atmosphere provides ample protection. Satellites might need extra shielding, power grids might require adjustments, but civilization would continue unperturbed. It would be a scientific curiosity, not a cataclysm. The geographic poles, on the other hand, are defined by the planet's spin axis, the imaginary line about which Earth rotates once every 24 hours. The north and south poles mark the points where that axis meets the surface. These two move, but very slowly, through processes such as precession, nutation, and true polar wander. None of these motions involve the planet suddenly tipping over or continents racing toward the equator. They're graceful, stately shifts, unfolding over thousands or even millions of years. The idea of an instant geographic pole shift where the entire crust supposedly slides over the mantle like a loose skin stems from mid-20th century theories that have long since been discarded. Early proponents imagined the Earth's outer shell could slip suddenly, relocating the poles by thousands of kilometres. It's a dramatic image, but the physics doesn't support it. The solid crust and the viscous mantle beneath it are coupled too tightly for such an instant rearrangement. Moving an entire planet's mass distribution would require an energy input beyond anything nature can deliver outside of a planetary collision. The genuine phenomenon of true polar wander is subtler and far more elegant. Over tens of millions of years, large-scale shifts in mass, such as the rise of mountain ranges or the movement of mantle plumes, can cause the whole crust and mantle to slowly realign relative to the spin axis. In effect, the planet rolls by a few degrees to maintain rotational stability, but this happens at rates measured in centimetres per year, not kilometres per second. The only witnesses are rocks, glaciers, and time itself. So where did the myth of sudden catastrophe come from? Partly from human storytelling instincts. We are drawn to transformation, to the notion that a single event could reset the world. Ancient myths often describe cosmic upheavals, the sky falling, the world turning upside down, night swallowing day. These are poetic reflections of natural cycles, eclipses, floods, seasons, magnified into metaphor. In the modern era, those motifs have merged with fragments of misunderstood science, giving rise to new forms of the same old tale, instant reversals, lost civilizations, and magnetic disasters just over the horizon. But reality, as it turns out, is far more interesting than any doomsday script. The poles wander, tilt, and even dance slightly from year to year in response to melting ice, shifting oceans, and the subtle breathing of the atmosphere. Scientists can measure these motions with extraordinary precision, down to millimetres, and trace their causes through data from satellites, GPS, and gravity sensors. The North Pole's path, for instance, has drifted steadily toward the British Isles over the past century, influenced by changes in Earth's mass distribution and core flow. These are not omens of disaster, they're clues about how dynamic and interconnected our planet truly is. Understanding these real motions doesn't make Earth seem fragile, it makes it seem alive. The magnetic field reverses because the core is a restless sea of molten metal, swirling in patterns that generate and sustain our planetary shield. The axis wobbles because ice melts, air moves, and water shifts, because Earth is always redistributing itself in search of equilibrium. The crust slowly slides and rebounds, continents drift, and the poles trace elegant spirals through time. Each motion is a response to gravity, heat, and the long memory of a spinning world. There's comfort in this slow choreography. It shows that the forces shaping our planet are ancient, steady, and self-correcting. Nothing in the data suggests a sudden global flip waiting to happen. What we do see is a planet constantly adjusting, never still, never catastrophic, but always beautifully balanced. The next magnetic reversal will come someday, as they always have, but when it does, it will be less a drama and more a whisper. Compass needles slowly turning, scientists excitedly updating maps, the sky unchanged. Perhaps the most fascinating part of this story is how it reminds us of our place in time. We live in one brief frame of a vast ongoing motion. The poles we know are only temporary, their positions shifting gently through millennia. The continents we inhabit will not stay where they are forever. Yet through all this movement, life endures. So when someone mentions a coming pole shift, you can smile and say, it's already happening, just very, very slowly. The truth is not an apocalypse, but a symphony of motion, so subtle it takes generations to hear. And that, in its quiet way, is far more extraordinary than any sudden end. A world forever in balance, always turning, always finding its way home to north. If the past has taught us anything, it's that the Earth is never truly still. Its poles drift, its crust flexes, and its oceans breathe in long planetary rhythms. Over the next 100 years, those motions will continue, quiet, graceful, and largely unnoticed unless you happen to be one of the people measuring them. The coming century will not bring sudden tilts or catastrophic flips, but rather a continuation of the same slow choreography that has been unfolding for billions of years. What will change, however, is how clearly we can see it. Let's start with what scientists expect to happen. The geographic poles, the ends of Earth's spin axis, will keep wandering at roughly a few centimetres a year. That may not sound like much, but over decades it adds up to meters, enough to keep geodesists busy, updating reference frames and navigators adjusting their bearings. The magnetic poles, meanwhile, are on their own lively journey. The North Magnetic Pole, currently racing across the Arctic Ocean towards Siberia, is likely to keep moving for some time, though its speed may fluctuate. It has covered more than 2,000 kilometres since the early 1900s, and there's no reason to think it will stop anytime soon. Still, this is an adventure of maps and models, not of mayhem. Compasses will adjust, charts will update, and pilots will calmly repaint a few runway numbers. These shifts matter because they feed into how we measure and manage precision, from mapping satellites to atomic clocks. The Earth's rotation continues to vary by milliseconds each day, influenced by the movement of air, water, and molten metal deep below. As polar ice melts and groundwater is pumped from aquifers into the sea, the distribution of mass changes, nudging the spin axis slightly. The overall trend suggests that climate-driven redistribution of water will become a major contributor to pole motion in the coming decades. Scientists have already observed the signature of this effect. The North Pole's drift since the early 21st century has tilted measurably toward regions losing ice and water mass, such as Greenland and western Antarctica. This doesn't mean the planet is tipping over, far from it. It's more like a gentle readjustment, a balancing act in response to shifting weights. The rate of polar drift may increase slightly as more mass moves from land to sea, but even then the motion will remain slow and predictable. What will change more rapidly is our ability to track it. Over the next century, Earth observation technology will become astonishingly precise. Satellite missions that already measure gravity changes and crustal deformation will evolve into constellations capable of tracking millimetre-level variations in real time. We'll be able to see the planet breathe, glaciers thinning, deserts expanding, oceans swelling as it happens. Reference frames like the International Terrestrial Reference Frame, ITRF, will be continuously updated rather than revised every few years, keeping pace with a planet that refuses to stand still. For the first time in history, we'll not only map the world as it is, but as it moves. This improvement will quietly touch everyday life. GPS and navigation systems will grow ever more accurate, compensating automatically for tectonic drift and polar motion. Surveyors and engineers will work in coordinate systems that adjust themselves, ensuring that the roads, pipelines, and buildings of tomorrow align perfectly, even as the earth beneath them shifts by centimetres a year. Farmers will see autonomous tractors steering along invisible satellite paths that take account of both geography and geophysics. Even smartphone maps may soon incorporate live corrections for continental drift, meaning that north on your screen will always be exactly where it is, and not where it was last decade. The same precision will help keep time itself on track. As Earth's rotation subtly changes, timekeepers will continue to compare UT1, the planet's actual spin, with UTC, the atomic standard. The need for leap seconds, those small adjustments that occasionally add an extra tick to our clocks, may eventually fade if international bodies adopt continuous time corrections instead. By mid-century, time may flow in a steady stream, its tiny imperfections absorbed silently by algorithms rather than announced on the evening news. The concept of a day will remain poetic and practical, even as its exact duration continues to fluctuate by a few microseconds. In aviation, the century ahead will see the quiet continuation of an already familiar routine: runway renumbering. As magnetic north migrates, airports across the world will repaint headings every few decades to match the shifting magnetic grid. It's a logistical exercise more than a crisis, a testament to how adaptable modern navigation has become. Satellite-based systems already rely more on true north than magnetic bearings, ensuring that long-haul flights cross oceans guided by stable celestial geometry rather than wandering magnetic fields. For those working in geodesy and earth science, the coming decades promise a golden age of clarity. The blending of satellite laser ranging, radio astronomy, and quantum-grade inertial sensors will produce a model of the Earth so detailed it will capture the sway of individual mountain ranges as seasons load and unload them with snow. The continent's motions, the steady drift of Africa northward, Australia's race toward Asia, will be charted in exquisite detail. Even the subtle Chandler wobble, the free swing of Earth's axis, will be monitored like a pulse. The Earth will no longer be a mystery of motion, but a carefully watched organism, its rhythms recorded with affection. Some speculate about more dramatic changes. Could melting ice sheets significantly alter Earth's spin rate? Or could a surge in earthquakes shift the poles more abruptly? In principle, yes, but on scales too small to disturb daily life. A magnitude 9 earthquake might shorten the day by a few microseconds. The collapse of a major ice sheet might move the pole by a handful of centimetres per year. These are monumental events geologically, but gentle ones geographically. The world won't notice in its daily spin, only in the long, slow redrawing of coastlines. For humanity, the real challenge and opportunity lie in how we respond to these quiet movements. As climate change reshapes rainfall and sea level, the precision of our measurements will help societies adapt, designing resilient cities, planning for shifting river systems, and monitoring groundwater use with millimetre accuracy. Geography, once a static science of borders and features, is becoming a dynamic discipline of flux and feedback. Our maps are beginning to breathe alongside the planet they describe, and there's something rather beautiful about that. The more the Earth drifts, the more closely we follow, refining our models and updating our coordinates. It's a partnership of movement, a restless world and a species curious enough to keep pace. In 100 years, the poles will not be where they are today. Coastlines will have adjusted, runways will bear new numbers, and time standards may have evolved into seamless continuity. But through it all, the sky will still wheel overhead, and the rhythm of the planet will remain as steady as ever, patient, ponderous, and enduring. So the next century will not bring a world turned upside down, only one measured with increasing grace. The poles will wander as they always have, and we will wander with them, a cartographic species on a living globe, tracing the slow heartbeat of home. If places feel steady, it is because minds are good at making them so. Streets do not drift beneath footsteps, coastlines do not race away during a morning walk, and mountains seem anchored for all time. Yet the quiet truth is that stability is a shared invention. Humans adopt reference frames, adjust charts, refine coordinates, and carry on. Airports repaint runway numbers, mapmakers update datums and epochs, navigators convert between magnetic and true north without a second thought. By constantly realigning measurement with motion, the world stays familiar even as the planet gently changes underfoot. Across these chapters, the choreography has been soft but precise. Precession sweeps the celestial pole in a vast circle over tens of thousands of years, trading one pole star for another in the slow passing of ages. Nutation adds the delicate embroidery. Short-period nods stitched by the moon and the sun, tiny tilts felt only by careful instruments. The Chandler wobble lends a free 14-month swing to the axis, excited by seasons of wind and water. Mass moves and the planet responds. Ice sheets grow and melt, aquifers are pumped and refilled, oceans shift their weight along invisible contours, and Earth adjusts its spin and figure by millimetres and microseconds. Earthquakes contribute brief, sharp edits. Tides and core mantle coupling write subtler lines. Through it all, time itself must keep pace. UT1 follows the planet's true turn. UTC holds steady to atoms, and every so often a spare second is slipped in, so noon in the sky stays close to noon on the clock. Maps are the translation of this motion into meaning. Global frames like WGS84 and ITRF offer positions with velocities, coordinates with birthdays. Plate-fixed worlds keep local surveys steady while the continents quietly stroll. Satellites trace gravity's whispers, radio telescopes listen to quasars, and reference points on bedrock breathe with snow in winter and dryness in summer. North is a family of ideas, magnetic for compasses, true for geometry, celestial for story, and navigation is the art of moving gracefully among them. At the end of the Earth, the poles are not dots but places, drifting ice, flowing ice, markers reset each new year, and long corridors of silence where instruments murmur numbers into cold air. None of this is alarming, it is reassuring. A planet that changes predictably is a planet that can be understood. The scale of drift is small, the precision of measurement is large. The partnership between the two is what keeps daily life untroubled. The wonder lies not in catastrophe, but in fidelity, in the way instruments, models, and traditions hold the world still just long enough to measure it, and then let it move again. So hold a last image, gentle and clear. Far above night oceans and sleeping cities, Earth turns, slow, steady and slightly askew, its axis tracing a patient curve among the stars. Winds pass their momentum to stone, seas answer back. The crust flexes like memory foam and then settles. Polaris keeps watch for now. Another star will take its turn in a different age. The planet keeps its balance by swaying, and in that small continuous sway there is peace. Thank you for listening. If a question or a thought drifted in along the way, share it softly in the comments. Where in the world you are listening from, or which part of this quiet motion felt most surprising. If this journey helped ease the day toward rest, a gentle like and a kind subscribe help future wanderers find their bearings here. And to all who are already subscribed, warm thanks. May the turning of the earth be a lullaby tonight,